Yeah.
Yeah.
All right, started the recording then. Well, I think that the special surprise guest today needs no introduction after we've devoured the lecture series on YouTube as well as the book over the past few months. There's Richard. Here's the rest of us. So Richard, we've been working through your Statistical Rethinking version 2 book over the last few months, and we just finished going through all of it.
Great.
And first of all, thank you very much for making all of it available for free online. That was majorly exciting and really nice for all of us, as most of us are PhD students, to not have to spend additional money on material.
Yeah.
And I thought we could just take some time to chat about a few things that came to mind as we were going through the material, sort of get your input on it. And if everyone has the time, including you, Richard, I asked people to, on a voluntary basis, prepare some quick presentations of what they've been doing so far, how they plan to do it Bayesian, to sort of get conversation started.
Super. Yeah,
Cool.
whatever you want. I've probably got an hour and a half, an hour 45 minutes, and so I have to be somewhere at 3 p.m. Central European time. So you're at the same time zone as me. Sorry, I like habitually, since I live in Zoom now, I just habitually say the time zone every time I say a time. So I got an hour and 40 minutes, maybe max, hour and 45 minutes.
That sounds just fine.
Okay.
So yeah, I think just to get the ball rolling, I'll just put one thing out there, and that was what we struggled with quite a bit. And as I was going through the exercise solutions that you have made available as well, I was always struggling a tiny bit with how to reparameterize a model from a centered to a non-centered version. And so the rule of thumb that I got to was just have only numbers down from the linear model in your model description. Yeah. But how I get there is not quite clear to me, and we haven't quite been able to understand that, all of us together.
Yeah, well, how do you want to? I sympathize with this issue because it is confusing. First of all, the terminology makes no sense, and it's another example of why statisticians should not be allowed to name things. But there are some, the basic strategy. Maybe I give you my abstract version of it, and then maybe we do some examples. I don't know how you want to do it. Would that be good?
So while you give us the abstract, I'm just going to pull out the reparameterization that you've done in the lectures, so we've got something to look at afterwards.
Super. So yeah, I think the abstract way to think about this is that a non-centered parameterization means that your priors don't have other parameters in them. And now why that's called non-centered, there's just no good reason for this, but that's just what it is. So you'd have constants in the prior rather than other parameters. So, and of course, so if you want to make a multi-level model, as all of you know, you need parameters inside of other priors. And so how can you make a multi-level model if you don't do that? And the answer is a little bit of algebra. And so you can smuggle parameters out of distributions by factoring them. And this is a case where I would draw on a chalkboard or something or type. But the simplest example might be something like, well, the Gaussian one is maybe the simplest. You think about a Gaussian distribution with a mean of 0, let's ignore the mean for a second, and a standard deviation of sigma. And if you divide by sigma, you get a standard normal. And then you can take those deviations on the standard normal and multiply them by sigma and get them back on the original scale, right? So what that amounts to is just taking sigma out. And then if you put sigma back inside the linear model, the prior is effectively has a scale of sigma again. But inside your model code, the prior you'll have a bunch of z-score parameters instead that are standard normals. And then inside the linear model, you multiply those z-scores by sigma. And that's mathematically equivalent to having sigma inside the prior for the random effect. Does that make sense? And that was the first example. Again, this is something where maybe I should type it, share my screen and type in a text editor, or I mean, you folks are in charge, but
I
me waving my
that would
hands
help
is
a
not.
lot.
Yeah, exactly. Waving my hands is like Sigma, and it doesn't really. So let me try to share
We
my.
could also use the whiteboard function of Zoom if you've used that one before. I know that drawing with a mouse is just very cumbersome.
Yeah, I'm not very good at drawing with a mouse, but if I were on my iPad, I'd go for that because I have a little stylus. But
So I have one question. So
yeah,
usually the example of why it's bad is like the funnel one, like the H school or whatever example you use. And
yeah,
and they're in like agency land. Like, so the argument is like by non-centering them, they're not like this, they're not correlated in the priors, and therefore you have like a better geometry. But it seems like what actually makes it work is in the funnel you have to take small steps down here and you have to take large steps up here. So it's more like to magically adjust the step size than the fact that the geometry gets better in terms of diversions, right? So there's there's some disconnect between like this geometry argument and the step size thing, which is probably why it actually works.
that's a good point. They're connected. So let's bookmark that, and I'll rehearse what I just tried to explain about factoring, and then let's come back to the step size issue, because that's a really good point. And okay, can everyone see my text editor?
Yeah.
Yes.
Yeah. All right. So what I've typed is just now is what I'd call a typical centered varying intercept type of thing. And the idea is you've got a model and these A intercepts. I mean, in rethinking notation, you do it like that, right? You put the little bracket ID thing on it. And then you've got a linear model, oh, sorry, up above this, right? Where, so say we've got some outcome and it's normally distributed with some mean, and I'll use tau now since I use sigma already. And then we've got AID plus some nonsense, right? Okay, so this is a varying intercepts model. Good, everybody? And so if we were gonna make the version of this, yeah, so let me make sure this is the centered varying intercepts model. And the non-centered version, top is the same, of course. And now what's going to happen is we don't parameterize on the A's themselves, although we can transform to get them. We think about the fact that each of these A parameters, AID parameters, is a product of some standardized deviation, a z-score, multiplied by sigma. And so we can write the prior like ZID normal 0, 1, because that's the z-score distribution, right? The standardized normal. And then up here we go ZID times sigma plus the junk. Yeah. And these are equivalent mathematically, but the sampling geometry is different because the sampling geometry in this model is much more, well, Gaussian in all directions. You don't get that curvature. The funnel doesn't appear. And so then whatever step size you choose, now we can loop back to the step size argument. Whatever step size you choose, it should work well in all directions. And the thing about funnels that's awkward is you're absolutely right. If you make the step size small, you can still sample them. But the whole chain becomes a lot less efficient because for much of the distribution, your step size is too small. And you're exploring, very slowly this big, vast plane of undifferentiated probability space. And when you're in the funnel, of course, your step size is super small. You're going to stay in the funnel for a long time. And this could mean the chain wanders and gets stuck in the funnel for a long time. And then you have to run the chain longer. Now, in theory, you can prove that, if you run the chain long enough, like theoretically until the sun swells and swallows the earth, you will get valid samples from the posterior distribution. But that's an efficiency consideration. The point that in principle, step size can solve the problem is a good one. It's just that, you've got to finish your dissertation. So it's like, yeah, getting rid of the curvature is makes everything easier because then it's a big limitation of Hamiltonian Monte Carlo that it uses a uniform step size. And there are, in theory, samplers that don't use a uniform step size in all parts of the posterior, but it's hard to get them to be reliable. They still require lots of tuning. And so what Stan uses is nice because it tunes itself and it tries to find a step size that works well. But if you've got a funnel, yeah, it's going to end up using a really small step size, or it might miss the funnel completely and not sample at all from it.
And that's when you get divergences, right?
Yeah, so divergences happen when you get into the funnel and the step size is too big. So you actually like break through the wall of the manifold, right? So the manifold is this curve. So now I'm doing this thing with my hands again. I apologize, but imagine an n-dimensional manifold, right? That's what this means, and it's a surface. And so in 3D, it's easy to imagine, right? It's like a bowl. And if the step size is really big, then so you're calculating a linear approximation to the movement of this particle, which is the combination of parameter values in this space. And it literally runs a physics simulation. So if in the chapter that introduces this in my book, there's that box where I have just plain R code and you can run the physics simulation. It's literally just a physics simulation. It's just Newtonian mechanics. And so that little particle, but you've approximated its path with little linear segments. And that's the thing. That's what makes it a simulation and not real physics. And if that step size is big, its step in that trajectory can punch right through the wall of the bowl. And then you get a divergence. And you can detect these things because this is a really nice feature. Sorry if I'm repeating stuff you learned already from the lectures, but I forget sometimes what I said in lectures. One of the great things about Hamiltonian Monte Carlo compared to the other Markov chain Monte Carlo techniques is it's because it's a physics simulation, there's a bunch of conservation laws that have to be true if it's working. And so you can check if it's working, for example, because energy in a physical system has to be conserved. So the Hamiltonian simulation is a closed system. And so the energy at the start and the energy at the end should be the same. And when you get divergences, they're not. And that's when Stan starts having a fit. That's how it detects divergences, is it checks that the energy at the end of the trajectory is the same as at the beginning. And again, if you look at that R code that's in that box in my chapter, you'll see that check is at the bottom of that loop, where that code that does a step, there's this check for the conservation of energy. And then it throws divergences. Divergences get rejected. They're not saved in the posterior. So in principle, they're not doing any harm, because like if you ran a Metropolis chain, you'd reject, sometimes Metropolis chains reject a majority of their proposals, right? This is one of the reasons they're so inefficient. So in principle, it's not a problem for Hamiltonian Monte Carlo to reject some divergences, but it's a sign that it might be missing or poorly exploring part of the posterior. So that's why it's not that, we get so spoiled. I do this too. You get so spoiled with Hamiltonian Monte Carlo now that you get like two divergences and you're like, oh God, this isn't working. But this is the luxury situation we live in now. When I was a graduate student, last century, we were writing our own samplers and we were rejecting 60-70% of proposals. Right. And Hamiltonian Monte Carlo almost accepts 100% of its proposals. And that's why it's so efficient. And the divergences are cases where it's rejected its proposals because it's the step size is too big. And that's nearly always because there's some part of the posterior where the curvature changes really fast. And there's a cliff or something, or that funnel. And those sorts of surfaces are hard to explore for any sampler.
A quick dumb question. So like in the ones that aren't HMC, there you would, as you said, you reject most of them, Metropolis, for instance. But you also expect to reject most of them. It's part of the game, right? Where like in ideal land here, you would never reject. But isn't it
exactly?
But the rejection criteria is probabilistic in the Metropolis output. Isn't it also like probabilistic in the HMC?
Yes, it is. It
and
is.
Isn't that kind of so you actually risk it actually not rejecting a divergent thing if you just get like an unlucky draw.
Yeah, you're absolutely right. And it has to be probabilistic for all the Markov chain criteria to be fulfilled. And Exactly. So it's the size of the energy deviation, right? There's always some in floating point land. There's these two values are always going to be different, and because no two floating point numbers are the same, right? And you can't test if one floating point value equals another. They don't.
But it's still like so because it's like 32-bit floats, you're gonna reject one in like 2 to the 32 just by random like rounding, and the rest of them you're gonna reject because they're bad. Is that a good intuition for what's going on?
Yeah, that's not bad. I mean, yeah, it's very, if you run these things long enough, you're destined to get a divergence. Yeah. I think that's the intuition that you want to get, and that's true, and that's not necessarily a problem. But we're running really short chains. I mean, if you take 1,000 samples and you get 10 divergences, that's not a chance. That's steep curvature someplace, and then not non-centering your priors or I mean, actually, sometimes I get problems because I forget to put a prior on a parameter. Like I'll be coding a model real fast, and I'll define a parameter, and then I'll forget to add a prior. And then some really bad stuff can happen. And you can get a lot of divergences there, because if you don't add a prior, what effectively happens is that's an improper infinite prior, right? The prior is the whole real number line, which you might intuit is pretty big. And if the likelihood, the probability of the data is not very informative for that particular parameter in that case, Stan is going to try to explore the whole real number line. And that's a very hard thing to do, right?
Well, those trace plots must look very interesting then.
They wander in completely weird fashion, and if there's a boundary on the parameter, like a scale parameter, like a sigma, you'll often get absorbed on that boundary, basically, because on the real number line projection of that. So maybe this is we're wandering in random directions here in these things, but in a Hamiltonian algorithm like Stan, every time you've got a bounded parameter, what's really going on is that Stan has defined another parameter, an auxiliary parameter that it's really going to sample, and then it's going to transform that to give you your bounded parameter. So for something like a scale parameter like sigma, which has a boundary at 0, that's a log link function is what Stan does. You declare lower equals 0 or lower equals any other fixed point, and it's going to declare an unconstrained parameter on the whole real number line and define the manifold from that and sample. And then what it reports to you is the exponentiation of that, so that it's strictly positive. Does that make sense? And it has to be that way because the Hamiltonian surface has to extend to infinity in all directions, right? It's a constraint of how the physics simulation works. And so you could actually, for any model with a lower bound explicitly defined in Ulam or Stan, you could just do it explicitly with a link function and get the same results. But that means if you wander near 0 for a scale parameter in sampling, Stan under the table, so to speak, could go all the way to negative infinity, and it'll look like the chain's not moving. Right, but it'll just look like it's stuck on 0, but it's moving. It's down because negative infinity is way down there. And so I've done this before. It's
so while we're talking about parameters and how they're transformed in Stan models, with the non-centered version of the model that you've just drawn up here, we would then want to retransform our understanding of the z-score and the sigma back into an alpha parameter, and we would do that in Stan in the generated quantities block, so it happens after each transition.
Yeah, so you could take so let's think about it this way. It's like defining another linear model. That if you want them saved, you need to do them in generated quantities or transform parameters. But if I took this model, non-centered version 2, and we could put AID here, but we need to define AID is equal to ZID times sigma. All right, so it's just like another definition. Yeah, and in Ulam, you can put GQ on the front of a definition, and it'll add it to the generated quantities block. I think there's one example in the text where I do this. I forget which one. But yeah, if you're just doing raw stand coding, of course, you just add it down there. But that'll report them back. In that case, you couldn't use it in the linear model. If you define it instead in transpars, transform parameters, then you can use it in the linear model just like this, and it'll also be returned in the samples. Does that make sense?
Now, yes, but now you're already going into my follow-up question to this,
Okay.
Which is what's the difference between generated quantities and transform parameters?
Okay, so a stand model, right? So you've got a data block, you got a parameters block. Then there's this optional transformed parameters block. There's also transformed data that's optional that can go in between data and parameters, but we won't talk about that right now. And then you survive long enough, you get the model, and then you've got generated quantities. Yeah. And as all of you know, everything. So what's optional? You need, well, I mean, in some principle, I think everything is optional. You can have just data and transformed data actually, and just spit things back. There's a bunch of weird stuff. Anyway, so what's the difference between these two? So parameters defines what the sampling is done on. So the stuff in the parameters block are variables that will define the manifold that the simulation is run on. And transformed parameters are functions of those parameters. And so in here, you define vector let's call it NID Z, right? And those are these Z scores up here. And a real lower equals 0 sigma. And then in transform parameters, you could go vector, sorry, I can't type, NID A, and you could say for I in 1 to NID AI equals ZI times sigma. And now this A vector is available in the model block. Everything in transform parameters is available everywhere else, just like the parameters are. Transform parameters are available everywhere parameters are. And they're also returned in the samples. So you have to be careful, right? You define too many auxiliary things with the parameters, you end up with a giant bloated result. But that's, so then in your model, you could, well, let's just finish the model. Do you want me to just finish the stand model? And
go for it, yeah.
Okay, so the priors are going to refer to the stuff in the parameters block, not to the stuff in the transform parameters block. In a non-centered strategy. That's why we're doing it that way. And so this will be normal 0, 1. And sigma, well, you got choices, but let's just use exponential. Yeah. And then you're going to have, we have our linear model, and it's going to be a vector of length n, and let's just call it mu. And we could do something like, for I in 1 to n, mu I equals AIDI, right? This bracket nonsense where you're embedding times sigma. And then, there's some other stuff in this model that we're going to leave as mysterious. But, and then at the end, you could have your outcome and go normal mu. And we need something other than we need a tau up here. Sorry.
But you have to set your prior based on the premises. So like if one of the premises were height, where you have like a good intuition for what the prior is on that scale, but not on the transform scale, then you actually have to like do manually transform it back so you can set the prior. Or...
Well, you don't have to. So for the non-centered, you can actually set priors on basically any symbol. Now this gets a bit weird, right? But this is an excellent question. It's if you know something about the transformation, but not about the underlying representation, then you want to set the prior in the transformation. But in the non-centered approach, the whole point is we want to define the sampling right? We want to set the priors on the underlying bowl-like geometry, which is what's in the parameters block, and not the whole point is not to have a centered prior. And the prior on alpha on these things is centered. It's got that, it could have a funnel. Yeah. And that's the point. But in general, you can set priors on higher level quantities, and probability theory being what it is, that'll trickle down. So an example that's really cool is this option in the RStan R. This is one of the options in that package. And
like R squared, as in like how, like
yeah,
what's the
the variance explained, forgive me for saying that, but you know, R squared, ye olde or R squared, as they say in the United Kingdom. And so there's this option in RStan R multiple regressions to set the prior on the R squared. And so the idea is that for many regressions in political science, which is, I mean, a political scientist wrote that package, they don't have strong information about each regression coefficient. But what they do know is for the sorts of problems they study, they never get regressions that explain more than 10, 15% of the variation. And if they did get more of that, they would know something was wrong, right? It's just like incomprehensible to them that they could explain all the variation and say armed conflict with a couple of regression coefficients, right? They just don't believe it. And so they wanted to set the prior on that. And so whatever, this basically means whatever the coefficients end up being, they shouldn't explain much more than, and you can set it, it can be 10%, 20%, whatever, of the total variation in the outcome. And that's a way of creating shrinkage on the regression coefficients, like in a multiple regression. But you don't apply the shrinkage directly to the beta coefficients. You apply it indirectly to some transformation of all of them, basically to their sum, right? Well, it's not their sum. There's a sum of squares criterion, right? You calculate these residuals and such. This is very well documented in the package documentation, by the way. It's a cool technique. And so that's an example, an accessible example maybe, but you can make up your own. You just have to be careful that you don't, do it wrong. But it's permissible. Yeah, as you learn, Bayes is very permissible. It's like, sure.
but in this simple case, let's say it was like IQ, right? So we would expect the spread to be around 15, right? No matter like how we shift stuff around, right? So we want to encode that, and now we've more standardized just that the set sigma, or like in your case, it's like sigma itself is that's the one you multiply by set, right? So we expect. I am so bad at reading these nonsense, but we would like right now sigma doesn't have a prior any. It has like exponential one, right? But I'm guessing we would so by just doing exponential 15, then we're good, right? Because
well, yeah, you want to change the scale, exactly. And if there's some scale, if you have information about the scale, definitely put it in the scale parameters.
But even if I put 15 in there, it's still going to be a non-centered model, right? So actually still good.
Yes. Yeah, exactly. I mean, you don't lose any of that flexibility when you do non-centering or whatever. It's just you've got to take the sigma. Basically, you're smuggling every time you create a non-centered version of a model. You smuggle the parameters out of the priors and put them back in the linear model, and it works for lots of distributions. Many distributions are factorable this way. Not all of them, but lots of them are. So scale parameters, nearly always you can do it because you can divide by the scale parameter and standardize the distribution, and then bring the scale parameter back into the linear model. It works for exponentials, right? So any exponential. So if I had an exponential here, like sigma, and then, say I had a gamma, because you can make hierarchical exponential shrinkage, right? So if I define a vector of sigmas and they've got a common mean rate gamma, then I need a prior for gamma. But now we've got a centered hierarchical prior, and then the sampling might be hard. There's no problem to just standardize that. And then you multiply sigma by gamma down here in the linear model. It's turtles all the way down, right? So does that make some sense? But to do it, you've got to look at the formula, the actual mathematical formula for the distribution, for its probability density, and see if you can factor out the parameter of interest by dividing. Typically, it's by dividing or subtracting. So for the Gaussian, if you subtract the mean, it's always centered on 0. And so many distributions, you can do that. You can subtract the mean and center them on 0. And if you divide by a scale parameter, you can standardize it. And that works for lots of distributions. Yeah, there are distributions where you can't do this, but yeah.
Sorry, this is pretty reminiscent of Russian nesting dolls to me.
Mm-hmm.
I was wondering, with the model at hand on screen right now, wouldn't we want to add tau to the parameters block as well, since we've added a prior for it?
Absolutely, we would. And
all right, cool.
I forgot tau until I got to the bottom, right? In typical fashion.
Yeah, no, I just wanted to be sure that the intuition was right there.
I should have made this Poisson, and then I wouldn't have needed a tau. But as we say, the fish distribution.
So the dividing by a z-score would work just as well for Poisson as well. That's one of the other distributions which you just mentioned. We can non-center like this.
For Poisson, with Poisson as an outcome, it won't matter. Count distributions, you can't really do much with them. Count as a prior, of course, in Stan, you can't use count distributions as priors, but for outcomes, it's all the same. You're in generalized linear madness land. You hook up your linear model to whatever ports are available on the likelihood distribution, and you go to work. Yeah, so absolutely. So we could get rid of tau here. This would be a better example, and just make this Poisson, right? And now mu is the well, we want to make it log, right? So we'd want to do exponent mu, and mu's on the log scale now, right? This is the thing about Poisson distributions, and their rates have to be positive. But yeah, and then with counts as priors, as I guess you've gotten to the end of the book, you can do them in Stan, but you've got to do all that weird averaging. That's it. I mean, no one asked about this, but what I would say about that is that that's a huge advantage, actually. I mean, it's kind of a disadvantage that Stan can't do it any other way, but it turns out in your life to be an advantage, because once you learn to do it that way, it samples way better than doing it the other way. It's very hard for Markov chains to do jumps, and with count distributions, you have to make jumps, and with discrete parameters, and it's very hard to efficiently explore discrete parameter sets. So you don't lose anything with Stan by having to do that extra coding. You get a lot of efficiency. You lose some development time, obviously, but it samples way more efficiently, and you're going to get much better samples. And then you can do the inversion, like I show in the text, and get the posterior distribution for the discrete parameters. So this has been like in I think parts of cognitive psychology, where they have lots of latent trait models, right? So you've got a bunch of individuals, and they have different strategies, cognitive strategies, and these are latent discrete traits, right? The types are considered to be discrete, and you want to estimate the probability each participant is in each state. They code those up in Stan now because they run so much better, and they used to use JAGS. Some of you are no doubt familiar with JAGS, and JAGS is great, don't get me wrong. It's an amazing piece of software. But once you put in the extra coding work to code up the latent state model in Stan, and it does require a lot more code, it samples so much better. And so that, I think there's this wave crashing across cognitive psychology right now, where everybody sees their colleagues use these latent state models in Stan, and they're like, oh my God, that's so much better. Yeah, because the typical JAGS chain for a model like that is going to wander forever, right? It's not doing a quite random walk, but it degenerates towards one, and so you got to run the chains for a huge long time. It's similar in what's that R package, MCGLMM? I think it's similar. People are taking 1 million samples, and it's just. Meanwhile, the equivalent Stan model, you need 500. So it's anyway.
So we get started on this code right here with the question of what's the difference between transform parameters and generated quantities.
Yes, thank you.
So no. I don't mean to stop you there.
No, bring me home.
Yeah. I'm thinking right now as I'm seeing this. I would probably want to use the transform parameters block so that the actual writing of the model is a bit more streamlined, because I can save myself the writing that I've already done in transform parameters block, right?
Yep. And you don't have to do it this way, but I think it's a good habit. I often write models this way. Maybe I can find an example, actually. Do you want to?
If you move to line 28 down to generated quantities, would it still work?
Line 28 down to generated quantities. You could not use A in the model block.
Yeah, exactly. That's what I was looking for. So there's a difference.
You would get them back, but you could use it. So generated quantities is appropriate for things that you want in the posterior, but you don't use it in the model block. So a typical case would be something like a correlation matrix, where you do all the calculations in the model block with the Cholesky, right? That Cholesky thing. And I don't know how people in Denmark say that name, but
I think Kuliski, but I have no
yeah, nobody agrees upon how to pronounce it. It's obviously a Polish name, but he was French, so I mean, whatever you like, right? But so those Cholesky factors are great for they're super efficient, and you don't need the full correlation matrix inside the model block to do any work. But often you want to interpret. I mean, I don't know about you, but I can't look at the entries of a Cholesky matrix and understand the correlations. You got to multiply them, right? You got to multiply it by its inverse. And so that I'll do in the generated quantities. You could do it in transform parameters as well, but that means in any particular transition during the running of your Markov chain, that calculation is going to be done over and over and over again. Right, because every time it takes a step,
even for the ones that get rejected, right?
Even for the ones that get rejected,
yeah.
And so it's just wasting cycles. Now, for a little tiny correlation matrix, that's not a big deal, and you've probably got 8 cores, and one of them's folding protein, and the other one's mining Bitcoin, and whatever it is that you're doing with your fancy machines. But for big models, it's not. Yeah, it's good to practice safe model construction, because even when you don't need it, because one day you will. Basically, that's my attitude. So yeah, you want to be picky about that. For stuff you don't need in the model block, put it in generated quantities. If you need it in the model block, put it in transform parameters. And I was gonna try to find an example for you. I think this is it. Hang on. This model, yeah. Okay, so I won't. This is a big model, so I'm not going to walk you through every line of code. But this is a project I'm doing with a colleague, and it's income data, so household income reporting. And there's a lot of nonsense going on. Here's a big transform data block, but we've got a parameter block, and we've got a transform parameters block, which is 3 times the size of the parameters block. And this is exactly Eric's point, is that all of this is just to make it easier for me to write the model block. So this is a non-centered model. You'll see this Cholesky factor, right? You know this from my lectures, and some z-scores, and the means of the varying effects, and then some scale parameters. And then what goes on in transform parameters is I declare all those things that are like the A parameter in the example over here. Right, so this big transform parameters block right here is just the multi-dimensional version of that with a Cholesky factor. So and this just looks more elaborate, because here's that weird Cholesky transform that you remember from the lecture. Yeah, this is the kind of thing, by the way, you just keep it in your notes, and when you want to write a stand model that needs this weird matrix algebra formula for getting to the original scale, you just pull it out. But all this does is take the Cholesky version and construct a bunch of varying effects that have the right correlation structure. And so this matrix V is a set of varying effects, a matrix of varying effects that has the correct correlation structure. And then I'm constructing a bunch of intermediate symbols here, which I can use to do things conveniently in the model block. Yeah, and I've declared P, mu, and S at the top of the transform parameters, so they'll be available in the model block. V, I have declared inside these parentheses, which means it won't be available in the model block. It won't be saved. It's a temporary, it's local. It's got local scope inside. You can do this and stand wherever you want. You just create curly braces, and anything declared inside those curly braces is local. And so this matrix V for me is not something I want to reference in the model block. So I declare it locally so it doesn't get saved in the posterior. Does that make sense? Anyway, I thought it might be interesting to show you, yeah, this is what I do. And it means that I have to write this nonsense. But when I get to the model block and I start writing my linear model, I can refer to these P's. And so here's the P thing and the S thing and the mu thing. I can refer to those when I need them. And this is a model where there's a probability the income gets reported, and then there's a distribution of the income. And so mu is the average income for the household. S is the standard deviation of their incomes. This is for a log normal, right? These are log normal means and standard deviations. And this is the probability of reporting an income on a given day. And so every household has these three parameters, and the goal is to estimate each of them. But they're all transformations, right? P has to be on a 0-1 interval. Mu has to be positive, and so does the scale. And so these underlying random effects get transformed here, and then all the code down here, I don't have to do that over again. And this cognitively for me is a lot easier because I do it once in transform parameters, but it would work fine if you did it all in the model block. Yeah. So anyway, I think this is what you evoked from me, Eric, when you asked your question.
Yes, that was exactly it.
Yeah. Anyway, so sorry, but yeah, so in my own project, that's the way I do it. I typically start by coding a generative simulation of the project, and then I write the stand model. I almost never use my own package, to be honest, but I wrote that package as a teaching thing. And although I will sometimes use Ulam to get to do the model, because it automates things like imputation and things like that, and that saves me a lot of coding time. But anyway, next.
Cool. Yeah. Next, let me quickly refer to my notes here.
I have to pick up my daughter. I will maybe try to see if I can join you in my car, but I won't be talking then.
Okay.
I'll keep an eye out for you in the waiting room.
Thanks.
Sure.
All right. There's a hand.
Go for it, Serena.
Thank you. I have a question that I think it may be kind of simpler to sort out, and this is about conditioning or controlling for a variable, in particular in relation to bias. So basically, from what I understand, if we have a let's say a regression, and then what does it mean to condition on a variable? Basically, it's just including the variable into the regression, into the model. And that means, so what happens once we know the value of the variable, right?
Yeah.
But then there is this example of selection bias as an example of collider bias, right? So in that case, conditioning means selecting. So that means knowing whether the data point was included or not. And what kind of puzzles me is that linguistically, these ideas are the same, but then computationally, when we code, is different, right?
Yeah, this is actually a great question, and it's very perceptive. And it's unfortunately, conditioning means different things mathematically in different contexts. But all these things get called, again, statisticians should never be allowed to name anything. But yeah, so this is actually a great question. So yes, it's to back up it in a simple benign multiple regression case, when we say we condition on a predictor variable, we simply include it in the linear model. But the right way to condition but in that same context, if the variable were a collider, you wouldn't want to condition on it. Yeah, and then your example, which is a very good one, is if we had a sample where it was conditioned on a collider effectively, so it had selection bias, we would also say it was conditioned on the value of that variable. And that means we have a data set that doesn't have any of the cases with the other values. And all of these things are called conditioning, and it's a nightmare. And so maybe I can be helpful by saying that, I mean, so this relates to these fights that sometimes, well, fight is a strong word, right? I mean, figuratively, these confused debates that happen between the Bayesian statistics community and the causal inference community in computer science. So let's call these factions Team Gelman and Team Pearl, right? If you know who these characters are. So from Team Gelman's perspective, which is this kind of now, you think about Gelman represents the applied Bayesian community globally, right? He's the most visible living Bayesian statistician by far. I mean, there's just nobody with his audience and his influence. And he's from this, like, you know, Ur, as we'd say in Germany, this Ur lineage of Bayesian statisticians that includes Don Rubin and others. And so he really represents this tradition. And in that tradition, the Bayesian tradition, it is axiomatic that you should condition on all information. Yeah, I'll say that again just for dramatic impact. It is axiomatic in that Bayesian tradition that if you have a variable, you should condition on it. Now, Team Pearl, as you know, has a different view of the axioms, and their view is, well, you draw the DAG and then you decide what you should condition on based upon the do calculus. That is, deciding what is needed to get an estimate of the causal effect of interest. And I teach that in my lectures, right? I'm a big fan of that. I'm also a big fan of Team Gelman. I love both of these teams. And I believe that there's really no conflict. It's just that what condition means in those two contexts is different. But Andrew and Yuta have gone at it on Andrew's blog over this exact confusion. So this is why I say your question is very perceptive, because you've gotten right at a fundamental like fault line between these different applied statistics communities. And the resolution to this is that in the Team Gelman version of to condition on, it doesn't mean put it in the linear model. Where you put it depends upon the DAG, actually. But the causal inference strategy in the Bayesian tradition, which goes back just as far as the computer science tradition, is you encode the whole DAG as a set of simultaneous equations. And there's an example in my book of this, right? So I think it's in one of the multiple regression chapters. There's this part where I'm saying, how do you compute the causal effect? And we put the whole DAG in the same model, right? You've got multiple linear models in the same model. I guess it would be QAP at that point in the book. And that's the old Bayesian orthodoxy, is that you take the whole DAG, every equation that it implies, and you code it up as a set of simultaneous equations, and you get a joint posterior for every symbol in the DAG. And that's what conditioning on every variable means to a Bayesian. Mm-hmm. It doesn't mean putting everything into one linear model. And so in that case, you could condition on a collider and it would be fine, right? Because you'd have a graph that knew it was a collider, and you'd be estimating the impact of that collider, of things on that collider, but you wouldn't be polluting inference of other parameters. Because the structure, the collider structure would be represented inside the QAP or Ulam or Stan model, and it wouldn't cause the bias because you had recognized it was a collider and you had coded it that way. That said, what's great about the Perl tradition is that it tells you the thing's a collider, and so you don't even have to bother coding it, right? And so you can just leave it out, and that simplifies our lives, and I think that's a good thing. But you can always just take the whole DAG and express it as a set of simultaneous equations and get away with it. And that's the structural equation modeling tradition is like that, but for linear models, for purely linear models. So the SEM crowd, if any of you are part of the SEM crowd, and SEM software like Lavon, if you know that, Lavon is this great package for making SEMs in R. And there's a Bayesian version called Blavon, of course, with a B on the front, which makes Stan code. And Blavon's strategy is you tell it the DAG and it conditions on everything, but it doesn't create that pollution effect of conditioning on a collider. Anyway, does this make some sense? And then, yeah, and then the do calculus version is the correct way to condition on something. Well, I mean, what the do calculus does is it produces a formula, and that formula has some symbols in it and not others. That's what Perl does, right? You get this estimator, and that you plug the information into. And if you have a really big sample, these approaches are equivalent. In finite samples, they may not be, because the Perl approach doesn't have any way to get uncertainty. Yeah, so I've drifted a bit, but it doesn't produce standard errors. It just produces point estimates. And so the Bayes approach, which I use in my book, is like this weird hybrid monster of using Perl's approach to say, look, we don't need this variable. Here's a risk of adding that variable naively to a regression model. And then using the Bayes engine to get full posterior uncertainty. But for every example in my book where we do causal inference and we apply the backdoor criterion or anything else, you could just take the whole DAG and code it in Ulam, and it would give you the same answer. Did that help? Sorry.
Yeah, thank you. That's very, I mean, it's super interesting because it gives so much context to the choices, right?
Yeah.
But my question is like, going back to the example of the sampling. So when in a way the DAG for the sampling, like for example the case on the projects that are funded, right? Because they're either newsworthy or trustworthy, scientifically trustworthy. So in that case, the DAG is something that has already happened. I don't know exactly. When we condition on sampling, meaning knowing whether something has been included in the sample, we have a DAG with a collider, but the DAG is something that's already happened before our model.
Yeah, exactly. That's a great question. So then it's missing data. It's like the missing data example from the missing data chapter. It's that your DAG represents the causal process that makes an observation observable. And then you're in the missing data algorithm land again, and you've got all these missing values, and the question is what caused them to be missing. And the thing about the collider selection bias case is it's the nightmare scenario that the outcome itself causes it to be missing, and then you're doomed. It's just horrible. But that you could still do stuff that way and represent it. There's these selection node diagrams too, which I didn't include in my book, and you'll sometimes see if you look at the causal inference literature on selection bias, there are these selection nodes as well. So the idea is that the population only has cases where certain variables have certain values, and that's what you're talking about. And yeah, so there's a whole thing about dealing with that, and yeah, in the pure Team Gelman Bayesian approach, you model that. The DAG includes those causal processes and you add them to the model. The Perl approach is often much simpler because you can use the geometry of the graph to say whether an inference is possible in this case. And that's nice. This is very important to me, by the way, in my own work, because I'm very interested in cross-cultural research, and cross-cultural research is often convenience samples, which are selected for particular demographic characteristics, not intentionally selected, but accidentally selected. And if we want to make comparisons between cultures and say how different they are, or how alike they are, this is really tricky when you've got convenience samples. It's so these sorts of selection diagrams are important to us here. And I mean, it's important even for more simple things like, I think development economists, they do a study in one place and then they want to apply it lots of other places. And then now you've got the same problem all over again, right? And if any of the way, say, education mediates income, if that's different across cities, then it's very hard to apply the results of an academic intervention in one place to another. Yeah, it's so this issue you're getting at, Serena, was that what your name? Are yeah, they're foundational to just like basic applied science problems, to my mind, and how we design school systems and all of this stuff. We make an inference in one place, and we like to use it in a broader set of contexts. And this brings up a bunch of new causal inference problems for us which are really about selection bias. Yeah. Anyway, you've got me riffing on selection bias now, which is a fun topic. Anyway, next, more.
Yeah, I would like to just make sure that I understand you. So basically, in the Judea Pearl approach, you use the DAG and you figure out what needs to be included and what doesn't need to be included, and you make one model and you're actually good to go. And in the Gell-Mann approach, you basically say, if there's 10 colliders, then there's basically 10 steps to my outcome, and you just make all of the models that goes all the way through.
Well,
and like simulate from them until you what.
It's almost the opposite, actually, is that in the team Gell-Mann approach, or the orthodox Bayesian approach, you have one model that's the whole DAG. You condition on everything, where conditioning means things are in their proper places according to the DAG. You get the posterior, and then you post-process the posterior to compute counterfactual interventions, which may include multiple paths. And that's like the example in my book, right, where we get the posterior, but then we're going to say, okay, now what's the impact of changing the marriage rate, or I forget what it was, right? But it was the silly Waffle House thing. And in the Pearl approach, you need, for every causal query, you need a different model. Yeah, or you might need a different model. So in the Pearl approach, what you do is you say, okay, what's the causal effect of interest, right? What's the treatment? What's the outcome of interest? Use the due calculus. The backdoor criterion is like a pocket version of the due calculus, right? It's a simple, for simple cases, you can just use that and see if something's admissible. And then that tells you the model you want to use to get an estimate of that particular causal effect. And then the coefficients in that model, the other coefficients in that same model cannot usually be interpreted as causal effects, because they may they're only in the model to control for things, right? To satisfy the backdoor criterion. Yeah, to block other paths, but they may be confounded. And so this is this thing that's called the table 2 fallacy. I don't know if I mentioned this in my lectures, but this is, in the epidemiology community, this is a term of art, that what they call the table 2 fallacy. It's a paper called the table 2 fallacy by Sander Greenland, and I think, and I forget who else.
And I take it means it's like all the things you control for you interpret them as causal, and they're in table 2.
Right. The table 2 fallacy is that every coefficient is interpreted as a total causal effect. Yeah, and this happens in lots of literatures, right? You get table 1 is descriptive. This is why it's called the table 2 fallacy. So at least in epidemiology journals, table 1 is a table of descriptives of your variables and average age and stuff like that. And then table 2 is regression coefficients. And if you present all of the coefficients in the same table without differentiating between which ones were used to design the causal query and which were added as controls, there's this risk that the readers interpret everything as a total causal effect. And so this is the concern of the table 2 fallacy paper. And it immediately, it's a great paper, by the way. If you haven't read it, it's got DAGs, it's short, it's really easy to read. I often use it as an introduction when I'm trying to get my senior colleagues to take this stuff seriously. I'll give them examples from the table 2 fallacy paper, because right away you get variables that need to be in the model, in the multiple regression. So these are simple models in the multiple regression to block a backdoor path, but the coefficient estimate that you get on that parameter is not a causal effect. It's some weird blend of a blocked confound and other things. In the most benign case, it's only a partial causal effect. Yeah. And because you've blocked a path with it. And anyway, it's yeah. So to summarize, maybe I've said a lot of stuff, so let me just back up and summarize. In the team Gell-Mann approach, you have one model and you get a posterior distribution, and then there's all this post-processing you do. But the number of post-processing steps is the number of unique causal effects you want to get out. In the Pearl approach, you front load that work. you have a DAG, and then you use the do calculus or the backdoor criterion, which is a special case of the do calculus, to create a list of multiple regressions you're going to run, and then each of those gives you those causal effects. But these approaches they should give you the same results. It's just the order of splitting it up. In the Gelman approach, there's one model, and then you split up the counterfactuals at the end after you've done the sampling. In the Pearl approach, you split the models up front. Does that make sense?
Yes, it makes sense. So the only thing is like it's like if there's 3 ways to block it in the Pearl approach, then it feels like if you could make like all 3 Pearl approach models, then you would maybe get like less error. I know that like he gets like only a point estimate, but let's just say that you're doing it in your way, where you actually get like posteriors for these things. Then do the Gelman approach actually gives you like more power because it does like the whole full posterior, like as if you made like all of the different submodels that could get that one estimate. Does that make sense?
Yeah, I see your point. Yeah, possibly. I don't know. I need to see a specific example and think carefully about if there are trade-offs. To be fair, so there's a direct answer to your question. I'm not sure. I need to think about examples and because there are subtle issues. But to be fair to the Pearl approach, there's this distinct advantage of it at times, is that you don't have to specify functions. So you can do it non-parametrically within some constraints, because a purely non-parametric approach with continuous variables is not possible, right? But if you had discrete variables with 2 or 3 values each, and you're trying to do some classification task, the fully Bayesian approach or any regression approach is going to require you to choose a bunch of distributions. Yeah, this is my class, right? You're just like, oh, now I need a distribution, pick one from the tree. And the Pearl approach, there are cases where you don't even have to do that to get a reasonable causal effect, because you can apply the do calculus, which is completely non-parametric, and get an expectation of a causal effect. Now, then you've got this second order problem, which I mentioned before, of getting uncertainties around that expectation. But in lots of benign cases, you just bootstrap. And now there's no bootstrapping in my book, and I can't think of the last time I ever bootstrapped a sample, but there's nothing wrong with it, right? It works. If it's a reasonably large sample, bootstrapping is going to work. It's one of those procedures that has no right to work, but actually does. Yeah. And
but like bootstrapping is basically like equivalent of having like a uniform prior on all of the points, right? So it gives you the Bayesian uncertainty estimate of if you actually have a flat prior. It's pretty amazing.
It is pretty amazing. And it is, pure typical frequentist bootstrapping has this issue that you can't sample any value that's not in the original sample. And that's obviously a little weird. So there's this thing called the Bayesian bootstrap that Don Rubin came up with, which deals with that. But that aside, if the sample is reasonably large, this is not usually a big problem. And the bootstrapping is very limiting in hierarchical cases, because it's not clear how you resample when you've got structured units, hierarchical units, right? Do you do the resampling based upon like whole classrooms of kids or individual kids? And that can completely change the answer. So there are lots of things where you can't bootstrap. Genomes, for example. Genomes have all kinds of weird structure to them, and nobody knows how to just randomly sample chunks in and out of a genome to do an analysis. But that said, there are lots of benign cases where
the whole point was that you could do bootstrapping when you don't know the function, right? So if there's a simple function but you don't know it, then you can do bootstrapping in the Perl. And in the Gelman approach, you have to specify some likelihood. For that part.
In the Gelman approach or any regression approach. So even, epidemiology is for the most part, almost no one's Bayesian in epidemiology. There are a few people, but they all use DAGs for causal inference. Not all, the vast majority. The big programs in Harvard, UCLA, they all teach DAGs, and but they're all frequentists, and so they're using parametric models for the most part. And when you look at the computer science folks like Pearl and his close colleagues, they try to postpone the parametric thing as much as possible because, well, they're trying to build robots that will, block out the sun and kill us all or whatever. I mean, sorry, I shouldn't make jokes, but they want to make robots that can produce causal inferences. They really do. This is what they want to do because I think that's how you unleash AI. And so that they're trying to see how far you can get without making those assumptions. Does that make sense? And it turns out for applied scientific purposes, forget AI, for applied scientific purposes, you can do a lot without distributional assumptions, really quite a lot. And that's good. I mean, for a scientist like me, it's not such a big deal because I feel like, my job is to build theory. I want to know what the functions are. Right. I mean, I think it's my job to figure out those details. And so, but for an applied person, like a development economist, that's not their job. Their job isn't to figure out how economies work. Their job is to help people. Right. If that makes sense. Now, obviously, if I knew how economies worked, I could help people even better. But there are people suffering right now. And they shouldn't have to wait for me to figure out the exact functional response. Yeah, and so you can get really far with the pure non-parametric approach if you have like humanitarian interest, I think. And so one of Pearl's colleagues, Elias Barnboim, has a whole paper about this actually, where he argues that it's often not necessary to worry about the parametric form, and he's got some examples. His papers are super technical because he's a computer scientist, but he's super smart. He's doing really, and he's very much interested in medical interventions. That's one of the things he's interested in. Anyway, I'm sure I cite a couple of his things in the book. Barenboim, he's Brazilian. Pearl's got a whole little cluster of brilliant Brazilian students, actually. I'm not sure how that social network got linked up, but anyway, sorry, every question you asked me, I've got like a lecture.
I think you answered most of my questions. I think it's thanks.
Yeah, sorry, I just, I live this stuff. So any question you ask me is going to be like, okay, so, do you want the 30-minute version or these are great questions. I can tell you folks have really digested this stuff because you're asking these like foundational, fault line sorts of questions.
I'm also doing a study group on the short Pearl book.
That's a great book.
The primer. Yeah. So like, if I can get you in as a sneak guest when we're done there, that would be amazing.
Email me. Let him see. We can try to schedule it.
I will. Thanks.
Yeah, that's a great little book. I thought about teaching a master's course at the university here in Leipzig using that book. Because there's no one in statistics here who teaches causal inference at the university. And so I thought about doing it. And the university here does a lot for me, and I almost never teach for them, and I feel bad, right? And so I should do some service for them, basically. Well, they give my students PhDs, right? And so I got to give something back to them. But anyway, so yeah, I thought it's a great little book. Basically, it avoids doing any statistics, right?
That's almost the worst part of it, right? Because I'm not well versed in probability theory, and we were all like we read it after your book, so we were all struggling exactly because we sucked at probability theory, but with decent applied statisticians.
Yeah, that's a good point. My book is the real cost of my book is I basically trick you into doing probability theory without realizing it, right? I mean, that's the whole. My book is getting you to do all kinds of fancy numerical integrals, and without realizing you're doing it, and all of that is justified by the probability operations and the axioms, but it's just been automated away from your attention. And that makes it approachable, and I think that helps it get a big audience. But yeah, then you get to these literatures like in computer science where you just got a page of probability manipulations and like trying to follow a do calculus proof, right? These little graph transformations all the way down the page. I don't know if you've been looking at the little primer, you've seen one of these or like where they prove instrumental variables or something, and you could learn that stuff, but it's a completely different skill.
I actually think like in the 3 first chapters, there's not the do calculus, as in there's only like how it works with graph. Like the formal rules to do calculus are not in the primer.
Oh, really? Yeah. I should go back and look at it. I blend all of Pearl's books together. Yeah, yeah, but you're absolutely right. I mean, most students have never had a good course in probability. So it's, yeah, and I certainly don't attempt anything in my book like that. We just get straight to coding. And then the computer does it all for you. It's just like magic, right? It's almost like you don't have to know probability theory. You just, the machine does it all. Yeah.
Just to get us back to what we've done in this study group, because I have a few questions from members still in an email document over here. Ruzan, you're probably best suited to ask that question yourself about histomancy that you sent me.
Yeah, so I was really amazed to read about histomancy, because we've been all looking at the final distribution of variables. So I was really interested to know about if not histomancy, then what's the solution to it?
If not histomancy, then what? Yeah, that's a good question. So
Yeah.
Yeah, so maybe I should answer this by saying first that, what's wrong with histomancy is that the sort of composite distribution of an outcome variable doesn't tell you what the conditional distribution of the outcome variable is, right? And GLMs, regressions, they only make statements about the conditional distribution, right? So the distribution, so like in a linear regression, you've got an equation for the expectation conditional on the predictor variables. And those models say that for fixed values of the predictor variables, the distribution is Gaussian. But those models don't say that if you take a total sample, a population of individuals or cases with different values of those predictor variables and dump them all in a bucket, that the resulting histogram is going to look Gaussian. And so that's why histomancy is a false god, right? It doesn't, it's just not principled. And it's a tradition, which is why I bring it up, because lots of people have been taught to do it through no fault of their own. I should say, by the way, culturally, this is an interesting thing, because biostatisticians are always shrieking about this. But in biology, which is sort of where I come from, I'm like a hybrid biologist, anthropologist, it's taught. I've had stats classes where the instructors said, this is what you do. You plot your outcome variable, and does it look Gaussian? Apply some test. If it passes the test, then you can use a linear regression. And unfortunately, that's just not principled. And biostatisticians know this. And in biostats departments, they just, wake up in the middle of the night in cold sweats because they know their colleagues in biology are teaching this. But
yeah, you actually just made me cringe there really hard because it's the residuals that we have to look at, not the outcome.
Yeah. So that exactly, it's the residuals. That's what I say. The residuals. So like in the frequentist perspective, it's the residuals that have that distribution, and that's after conditioning, and it's not the total histogram, and histomancy is the total histogram. In the Bayesian approach, it isn't even true that the residuals have to have that distribution, because it's just a prior, right? The likelihood function is just a prior for the residuals, but the posterior distribution of the residuals does not have to be the same as the prior, just because the posterior never has to be the same as the prior, right? So that's the frequentist approach makes much stronger assumptions about the nature of a likelihood function than the Bayesian approach does. And that allows it, now this is not your question, but you've tricked me into saying something nice about frequentism. Because frequentism makes such stronger assumptions about the likelihood function, this means it can compute things from the residuals that are unlicensed in a Bayesian approach. So now, of course, Bayesians are free to make the same assumptions. Bayes is permissive, right? It accepts all into the congregation. And frequentism is a special case where you make stronger assumptions about the natures of residuals. But like p-values, for example, to compute a p-value, you need to make assumptions about the sampling distribution, in particular, the tail of the sampling distribution. And in the Bayesian approach, you're not obligated to make the assumptions that allow that. And so to get a good estimate of the expectation, for example, and how it depends upon the predictor variables, you don't have to make strong assumptions about the distribution of the residuals. And that's what I teach in my book, right? So we're after the posterior distribution of the expectation. And that doesn't depend upon the residuals actually being Gaussian. And then as you know, because you've gone through my course, what does the Gaussian likelihood mean? It's a prior distribution that spreads probability as evenly as possible for any variable with a mean and a finite variance, right? And that's the maximum entropy interpretation. It's the flattest prior possible for a variable with only those features. But the posterior distribution of residuals can be lopsided, and you can still get a good estimate of the expectation. It works. And I mean, and since you've gone through my course, you know that you could do this, right? You could simulate values from an exponential distribution, which is definitely not a Gaussian distribution. It's bounded at 0, for example, and the mode is lower than the mean, right? It's a very simple example, something that definitely doesn't look Gaussian. But run a linear regression on it, and you'll get the mean. I promise. It'll have no trouble estimating the mean of that exponential distribution, because that's what a linear regression is to a Bayesian like me. It's a little robot that estimates the mean. And that's the strongest interpretation I'm usually willing to give it. But if you want to go further and say, I'm claiming that the residuals are actually Gaussian, then you can compute a bunch of cool things. Yeah, and that's what frequentists do. And it's just, I'm hesitant in the areas that I work in, I'm hesitant to do that. But there are certainly contexts in which that's perfectly safe. Yeah, so I'm not against it. Anyway, you got more than you asked for, but so now what do you do instead? Well, I like to use maximum entropy. I like to say, okay, for this outcome variable, what are the constraints on it? What do I know about this variable before I've seen the actual values of it? So for like something that's bounded at 0, that's information. And that gives you an idea of the kind of distributional assumption you want to make about it. And so then the maximum entropy approach is to say, given those constraints, what are the conserved quantities about these values? And this will be something like bounded at 0, finite variance. Then maximum entropy, you can just look it up in tables, tells you the distribution which spreads probability as evenly as possible, given those constraints. And so for the Gaussian, it's mean and finite variance, but unbounded. And then the other distributions arise from other types of constraints like that, like the binomial. The binomial distribution is the maximum entropy distribution for counted things with a constant expectation of success for each trial, and that's how the binomial arises. And that's again,
how do you get to the over-dispersed things? How do you get to a t-distribution from this?
Great question. Yeah, how do you get to over-dispersed things? So over-dispersed things arise from mixtures. So this is one way generatively to get them, and the way I think about them, you get like an over-dispersed binomial or to a t-family distribution, because so for the t-family distribution, it's a mixture of Gaussians. So there's some heterogeneity underlying population that you haven't measured. You don't know the labels on the different Gaussians, but they may have different variances. But when you mix them together, they're going to look like they're going to have thicker tails, and that'll give you, and that's one way to derive the t-family of distributions. And you get over-dispersed count models a similar way. There's heterogeneity in the underlying, there are labels that you haven't measured. They're like predictor variables, but they've been censored and you don't have them. And the cases that have those different variables, they have different expectations. And when you mix them all together, you get over-dispersed distributions and counts. So you can still, it comports with the maximum entropy approach. I'm a big fan of those mixture things all the time, absolutely. So for Poisson models, for example, I work a lot with ecologists, and in ecological data, there's lots of count data, and most of it's count data, I think. And I've never seen a count variable which is not over-dispersed. I mean, I'm trying to think of an example, and that's because there's lots of heterogeneity in the populations that we've essentially haven't observed it. So we don't have a homogeneous Poisson variable. Yeah. And then you can cope with that with these gamma Poisson, like mixture models, like I have in my book, or you can use hierarchical models where you've got random factors in the linear model. yeah, that go by the case or the unit or something like that. But it depends upon, the right thing to do will depend upon the details, unfortunately. And I refer you to the horoscopes chapter in my book where I get philosophical. But yeah, that's a good question. It's that said, now I'm a big fan of the maximum entropy approach, but that's not the only approach that makes sense. I think there are lots of legitimate ways to do this. And so sometimes there's this purely generative way to figure out what the outcome distribution should look like. There's this biologist, I think is at UC Irvine, Steve Frank, who used to work on cancer biology, and he got really interested in sort of the life course of cancer in an organism. And so one of the major things, if you're trying to model that, is the age of onset of cancer. So, I mean, in principle, like if an organism, why don't we have immortal organisms? Well, cancer is probably a good reason, right? And so in theory, if an organism, you know, could live forever, eventually cancer will start. And so you want to model the age of onset of cancer. And Steve Frank has a series of really cool papers where he has a purely generative, scientifically based biological, like cellular model of the age of onset of cancer. And it turns out to be gamma distributed. But it comes completely from scientific foundations. And now it's cool is at the end of the paper, he says, we could have anticipated this for maximum entropy. And then he talks about the constraints on it, which I found very satisfying, you can imagine. But he derives the whole thing from a real causal model of how this works. And the model is that, well, things break inside the cell, and cells have a bunch of defenses, a bunch of firewalls, if you will, against cancer. And you need a certain number of them to break. And so if you've got a machine and it stops working only when a certain number of things break, it turns out you end up with the time to breakage turns out to be gamma distributed. And this is what he proves mathematically. And he gets this. And then there's tons of data from laboratory studies of cancer, and mostly in mice, of age of onset, and it matches super well. I mean, the age of onset populations in clonal lines of mice to cancer are gamma distributed. It's a cool, so this is science, right? Not like what I do. This is like real science. And anyway, sorry. I mean, like I said, I've got like a lecture on all these things, but and then, you know, there's nothing wrong with guessing. And, I mean, I shouldn't say that, right? You're recording this, but look, a lot of scientific work is, I don't know what to do, but I got to do something. I'm going to try this thing and see if it breaks. And that's fine. It's just you need to acknowledge that publicly, right? And say that I didn't know what to do here, and I thought this was a relatively safe thing to do. I did it, and then I checked what it did to my inference, right? Or you could do robusticity analysis, try different assumptions, and see if they give the same answer. That works too. And honestly, a lot of science is like a drunk walk through history, right? We're trying to figure out what the right thing to do is. Yeah. Anyway, that's my candid opinion. Honestly, mathematics doesn't have any unimpeded access to reality, and so that means that this is just fundamentally hard, and we're all guessing. And I try to adopt some justifiable work procedure that will work most of the time. But if you have expert knowledge of your system, you should use it and not appeal to any general maximum entropy principles or other things. Yeah, that would be my urging to you.
It seems like you have to know something to actually appeal to general entropy, right? Because you can't really know whether it's overdispersed or not without knowing something about it.
Yeah, I think that's true. I mean, for basic research issues, that's absolutely right. And then there's this kind of lots of contexts in which we'd like to make inferences. Decision makers are worried about asymmetric error. And in those cases, there's lots of good reasons to always assume overdispersion, right? Because the tail events are, so this is Nassim Nicholas Taleb, right? And that crew, there's a bunch of these people, and they're not just in finance, but who basically think that even if something isn't thick-tailed, you should assume it is, because there's an asymmetry of costs. The extreme events can really be bad. And for an organism in a realistic ecology, assuming things have thick tails is probably the best thing to do, because if things don't have thick tails, you still do pretty well. But if you assume things don't have thick tails and they really do, it can be really bad. And so this is the investor. There's a whole community of investors. It's not just Taleb who work this way, because the extreme events in markets can ruin you overnight. And market growth is not additive; it's multiplicative. So if you get ruined, you're ruined, right? you don't. That's this interesting thing. Additive systems, you can recover in additive systems very quickly, but in a multiplicative system, you can only die once, right? Think of it that way. And so tail events in multiplicative systems, like growth systems like markets or populations, assuming there's a thick tail of risks is a prudent thing. And you won't regret too much if the disaster doesn't strike. That's the idea. In basic research, it's like a different issue, right? It's like I'm just trying to figure out what's true, and then I need some domain knowledge to think about the homogeneity of the distribution or something like that. Anyway, again, you provoked another lecture from me, but it's I think I have this luxury of being a basic researcher. I'm just trying to figure out where humans came from. None of my science gets applied to anything, right? And that's a real luxury. It's an absolute luxury, because there's all this decision theoretic sauce that's going to get poured over your statistical inference that really matters. And that has to do with managing asymmetric risk and cost and benefits and a bunch of other stuff, which is absolutely crucial. And I think, anybody working in education or criminology or really hard fields like that, where, the stuff they put in journal articles could get picked up into policy real fast, man, I'd be really stressed if I worked in those fields. I'm very relaxed in human evolution. But I mean, don't get me wrong, I love what I do, and it matters in the sense that where our species came from. I mean, that's a big question, but I don't think it has a lot of welfare implications. Yeah, so that gets me off the hook.
Maybe a bit of a palate cleanser right in the middle of this, with a less philosophical question. So the other peeps in the group have heard me bitch and moan quite a bit over the last few weeks about running into C-stack trace errors when executing multiple stand models in really short succession. I was wondering if you had run into the same thing.
No,
Right.
I've heard of this. I have colleagues who have this problem, but it never happens to me. And I don't know why, but do you use RStudio?
Yeah.
Yeah. Well, I'm not prejudiced against RStudio, but I don't use it. So that's the most conspicuous. I run things just in separate terminals.
Right.
So I have a separate terminal window open with different sessions. And I do a lot of my work on a computational cluster as well here at the Institute, where I'm just tunneling into the cluster and I have jobs running. And I mean, some of these jobs take weeks to run, right? So I don't run them on my computer. But I've never had this problem. But people email me with this problem all the time. And I'm sorry I can't be more helpful. But maybe try outside of RStudio and see, because RStudio has some middle stack where it interfaces with the terminal. And I had a colleague here in my department who had stand code that wouldn't run, and he was using RStudio, and then we just ran it outside of RStudio and it ran. So this is what leads me to wonder.
All right, I'll try that. Thank you.
Yeah, don't get me wrong. I think RStudio is one of the best things that ever happened to the R community. Right?
Yeah, no, what I ended up doing, so it only really came into play when I executed it through R Markdown.
Oh.
And I assume that this is, I read up on this a bit, and I found that other people would run into the issue with other packages. Usually it came down to overwriting the same model object by name with a new stand model. And apparently there's some end pointer on your hard drive, which just gets updated ever so often. And when it's not been updated again, then you can't assign the stand model to that. And apparently R Markdown, I guess this is all just conjecture, but it seems as though R Markdown only ever puts one pointer up and then immediately just fails on the next stand model.
Oh, wow. Okay.
So I just ended up brute forcing it and running everything in RStudio because that went well. And then just loading in these saved
okay. So it's an
model
R
objects
Markdown.
back into the R Markdown execution.
Well, yeah, well, thanks. That's useful information. I'll make a note about that when this happens to someone next. I also don't use R Markdown because I'm a dinosaur and I do everything in raw LaTeX. But I started, you folks have to understand, I started using R in the year 1999. And there was none of this RStudio, R Markdown stuff in 1999.
Well, it's a shame. It's a shame that Ollie, one of our participants, had to log off already because he's younger than that.
Yeah, exactly. So it's yeah. Now that said, R hasn't changed that much since 1999. I mean, it's remarkably stable, and I mean, there's a million packages now that do everything. But anyway, yeah, these are. The other thing I recommend to everybody, and maybe some of you do this already, is to use command stan as your interface instead of rstan, the command stan R package. And so with my package with Ulam, you can add command stan equals true as an argument and do it that way, but you have to install the command stan R package instead. And this bypasses all of that pointer stuff. Because it doesn't use R to manage the sampler at all. It just uses the raw command line. And I found this solves a lot of problems. It also, command stan is more up to date than rstan. So obviously there's one stan project and you're probably thinking like, what is he talking about? Why is he saying stan over and over again with different letters of the alphabet in front of it? But there's, so stan, the engine, the library, the stan library is just a bunch of C++ code. And that
heading out?
Yeah.
All right. Have a good weekend. Will you be in this weekend or?
Okay,
So,
sorry about that.
That's okay. But so and that gets compiled on whatever system you're running it on. And then there's the front end and how you use that. And so you can use stan completely from the command line. The shell, right, the terminal, just by compiling the source code. And when you use it through R, you're just using the R as an interface to execute those commands. So rstan, the package rstan, does that in a particular way that uses this package in R called rcpp, which you will also have installed on your systems, which has lots of advantages because it keeps objects in memory and then R can interact with them directly and extract their variables. So if you use rstan, you can do a bunch of fancy post-processing with it. And that's the way why they wrote it that way. It's very useful because it allows R to actually see inside the C++ code and pull things out. It's very powerful. With command stan R, it doesn't do that. Command stan R is very bare bones and it just executes the terminal commands. Command stan runs in complete ignorance of R even existing, dumps all the samples to your hard drive in a CSV file, and then reads them back into R. And that's what command stan does. And the virtue of this is that none of this extra nonsense can go wrong, right? There's a bunch of stuff that could go wrong because of rstan that can't possibly go wrong with command stan R because it never happens. And now that means there's some fancy post-processing stuff that you can't do with command stan R. But most of the time you don't need that. And it works fine. And then the other virtue is that command stan is always more up to date than rstan, because as soon as the stan team does an update of the stan math library, command stan R is up to date. Because it's nothing, it just is that. It just is the stan math library with a little bit of a makefile system on top of it for compiling the models. Whereas rstan, they have to then update, the glue that connects the rstan package to all of that. And then the worst thing, they've got to submit it to CRAN, right? So the Comprehensive R Archive Network. So CRAN, when you visualize CRAN, what I want you to visualize is a dark tunnel beneath the earth. And you will walk down this tunnel a few miles, and then you will enter a dimly lit chamber. And around a circular table will be a bunch of statisticians wearing robes, and their faces are obscured, but they're all angry. and you will lay upon this table your code, and then you will back slowly out of the room. And right, so this is CRAN, and don't get me wrong, CRAN is.
Sorry, I'm currently in the process of submitting a package to CRAN, and you described this quite adequately.
It's exactly like that, right? And they'll send you a nasty note afterwards, right? You submitted it, and there's one thing you've done inappropriate, and then basically they hurl objects at you. And they're famous for being rude and judgmental and lots of stuff. Now that said, CRAN is fantastic. It's they have really strong standards. And that's one of the things that makes the R community so great, is that everything on CRAN works together, because they have, the review process is very strict, but it means it's slow. And so it can take a long time because often, I've worked directly with the stand development team because I've funded them out of my institute. We bought programmers for them and stuff. So I'm a big supporter of that project. And so I have some inside access to the team, and I've heard their nightmare stories about submitting to CRAN. And it's not their fault, because anything that interacts with an external compiler, it's got to compile on all systems. And so when you submit something to CRAN, they've got basically, in that dark chamber under the earth, they've got a bunch of standard computing systems. Some of them are, ancient, from the 1990s. And all your packages have to be compatible with all those things in an array of compilers. And there can be weird compiler incompatibilities, and you have to figure it out before your package will get accepted. And so with a complicated package like RStan, this can take months for them to figure out. And so anyway, this is just a long monologue to say, if you use command stand, you get the updates right away. And some of the new updates on command stand make it significantly faster. So compiling through command stand, it compile in a fraction of the time. You get the latest bug fixes and features. So for example, there are these profiling features in the latest versions of Stan that I still don't think exist in RStan. And anyway, so you asked an innocent question, Eric, and you got my weird fan fiction about CRAN, but the wizards under the mountain. But I should write this up as a short story sometime. But
it definitely sounds like you could make a children's book out of that.
Yeah, so yeah, exactly. There's this famous developer, Douglas Bates, who was one of the original developers of the LME4 package, and he quit the R community because of how hard it was to get stuff accepted to CRAN. And now he works with Julia. He makes packages for Julia. But he had this very public falling out with the CRAN wizards under the mountain, and he's a bit grumpy himself. So but anyway,
that's the tale of the unstoppable force and the immovable object.
Exactly. I'm gonna have to go in a few minutes. Does someone have a last question or want the last word? Or
I have a last question, but I think if there's more on Eric's list, I think they should take priority.
We've actually just cleared the list, so
okay,
you
perfect.
feel free to go ahead.
Super.
So how do you feel or think about Bayesian circuits? So there's these where basically you have like a prior on all kinds of weird messed up functions, and then you just learn all of the latent stuff, like how you factor your matrix and all that stuff, like from this really messed up complicated prior. And that's like not at all like this maximum entropy thing.
Yeah, that stuff can be super useful. Absolutely, these non-parametric engines that are trying to learn function spaces, right? And Gaussian processes are an example in my course. I think of what you're talking about. Yeah. And these things are great. There are lots of applications where they're super useful. And you're absolutely right that they don't fit the stereotype maximum entropy approach. But different approaches have different features and uses to them. They're really good in lots of cases, I think. Those sorts of latent space function estimation things, splines, GAMs, a huge range of things. I mean, deep learning, right? Neural networks, not exactly the same thing in a sense, but if you squint, they're part of the family. Those things are amazing and super useful. And my only hesitation, I mean, what I'd say before vanishing in a puff of smoke here is you have to think carefully about what your goal is, right? So I think doing causal inference with those sorts of engines is very limiting, because, think about like a neural network. You can train it on a big sample of images, and it can produce similar images and all kinds of stuff, but it has no causal understanding of what's going on. And but they're great for prediction systems. So for building big, robust prediction systems, those devices are fantastic. I mean, we have a project here at my institute where it's just a bunch of old documents written in basically, medieval Danish. Actually, they're old parish records from Danish churches, and we just want to get them digitized. And it's this, it's cursive, right? It's this big loopy kind of stuff, and we just trained a neural network on it, and it reads them. I mean, it's just incredible. I just downloaded PyTorch and gave it some medieval Danish, and it's like, okay, now I know medieval Danish. It's like in the Matrix when Neo wakes up and it's like, I know Kung Fu. It's like my neural network knows medieval Danish, and but it doesn't really understand it, right? It just knows how to translate the cursive into ASCII, but that's all I want. That's really different than a basic research problem where you're putting in a bunch of causal information, whether it's structured as a DAG or structured as some other kind of generative model, and you want to learn about, the bits of that system. In that case, I think those general latent space sorts of solutions don't do a lot for us. That said, there may be components of your model which you want to just push off on those Gaussian processes or whatever. So I feel this way about. We have a project in my department which is studying child growth in communities in South America, and there's many aspects of the growth process that we're not interested in. We're interested in stunting and the effects of stunting. So we're just trying to detect stunting events, but the details of the biological nature of growth are actually not interesting to us. And so we can assign a lot of stuff to Gaussian processes and get away with it. Right. So it's like there are bits of the problem we want to bring into scientific focus, and then we make parameterized models, generative models of those components. And then there are parts we just let blur out. And all that matters is that we get something that's descriptively good. And then Gaussian processes and other sorts of daemons work really well in those cases. Sorry, did I answer your question?
Somewhat.
Yeah, sorry, I'm gonna have to vanish now if I'm.
It's fine.
If I'm gonna get to my next meeting, but yeah, I'm very permissive. I mean, I think there are lots of really cool machine learning tools, and they do great stuff. It's just if you keep your eye trained on the issue of like, is this a prediction engine or is this a causal inference engine? And how could these predictive tools be used to enhance causal inference? Then you can do lots of cool things. But keeping that distinction clear, let's just say there's lots of people in the machine learning community who don't know this distinction exists, and that makes these things dangerous, right? Yeah. Okay. I've had fun. This is much better than the other work I do in my life, chatting with groups of you. I should stop sharing my screen. We've had my text editor up there forever. Anyway, I'm going to hop on my bicycle and go to my next appointment. But you're all free to send me email if you got questions or you need anything. Okay?
Yeah, sounds good.
All right.
I think I speak for all of us in saying thank you very much.
Yeah.
This has been fantastic.
Yeah, it's been a joy.
It was a ton of fun.
Okay. Bye-bye. Take care.
Take care.
Bye.
Bye. All right, guys. I propose we just take a 5-minute tea break here. I'll pause the recording in the meantime. Totally, let's chat a bit, and then we just reconvene with the short presentations.
Sounds good. I'll switch from my phone to my computer then.
Recording, yeah. Quick show of hands. Who has got a tiny presentation?
Nice.
Cool. That makes 3 of us. Bernd or Rusan, who of you wants to go first? Because I'm just going to go last so I can then go straight into what do we do now with the group.
Well, yeah, I think I'm gonna finish it first. Let it.
Go for it.
Can you guys see my screen?
Yep.
So, hi, my name is Rosan, and I've been coming to this session for quite a while now, and one of the for the reason to understand this creature, and yeah, and I'm really enjoying this sessions, and there is a great value in knowing this creature in more detail. So to use what I've learned, in this session. So I've been thinking about this two different topics: personality and marketing. These are two very different topics, but if you study what links them, you'll find a great if you understand a link between these two topics, then you can find a really useful things. And so first one is the personality, and which can be measured in this 5 dimensions, and I'm not going to go into these details. And the interaction with our environment shape these personalities, and which then shapes our drives, and which then encourages us to buy some object. So it's like, for example, if you are high in neuroticism, then you'll probably end up buying a lot of products that's relates to safety, like insurance products and other safety products. So what's fascinating here is if you look at this from the object's perspective, and you'll see that there is the object already knows that it's going to be bought by you, that it's like some intrinsic value of the object that tracks some categories of personalities more than the other. So this is just an beginning of an idea, just a fantasy, and so this is why I have to include this last slide, because I cannot take any quick questions about this. And so thank you.
You're welcome. Your slides are amazing. Like you're really good storyteller.
Yeah. But
go ahead.
Sorry.
Yeah, go ahead.
No, just telling I was like not too much into the stuffs about what I said. I don't know. So that's why I can't talk about it more.
No, but it makes good sense that you want to use objects to predict the 5 categories of people, because then you can like do the reverse problem for future products, right?
Yeah.
That seems super neat.
So actually, I'll send you I'll send you a paper. I'm kind of familiar because you're talking about drive and motivation. So I'm familiar with the theory of motivation, and I'll send you a paper. I'm just you got me thinking, because this theory is about like 2 fundamental motivational states. But what if we're talking about the objects? I mean, can we?
Yeah.
So it's a cool way of thinking about it. I'll send you a couple of papers, and then you can tell me.
Yeah,
what you
this.
think.
Yeah, but I've been looking at not quite much, but it's like there is like this fascination that if you the objects, the real intrinsic value, it's like destined to be bought by someone. It already knows that it's going to be, that you're going to buy it.
It knows the distribution of people who will buy it.
Yeah.
That's also like common for design. If you think of like design, if you think of like shavers, for example, and then you see these smooth and round shavers in these more palish, pinkish colors, and then you see like, okay, that's the one more designed, the object more designed for like a more of female, like in, I don't know, or any transgender or queer who identifies with a more female identity. And then there are these male ones which are like more like this blue and then just square, just like more functional. So it's also like it's not only for personality in object, but it's also very common in design to think in both directions.
Yeah, there's one interesting experiment about this. If you place a really shiny crystal object in a room, the kid is probably going to go and touch it. So yeah, it attracts every person. So I think this is it.
I think that was grand. I don't really have anything to add to what others have said so far. Bernd, should we just go over to you then?
Yep, I'm trying to get my less beautiful presentation screen. I had really like mixed feelings seeing Richard here and thought like, oh no, I should have prepared my presentation in more detail and with a lot more care, but now he's gone again, so.
Well, I'm sorry for putting you into that mental turmoil.
Yeah, but now I'm fine again, I think. So I think you can see the slide at least, or the screen. So yeah.
Yeah.
But can I put the laser pointer? Yeah. So I want to talk about, I'm a plant biologist and ecologist. So my idea was to use these Bayesian approach somehow in linking phenology, so when plants are actually flowering to above ground competition. So on this very pixelated picture, you see like a meadow. And what you can see is that there's like a vertical structure. So plants, they flower to reproduce and they flower at different time points during the vegetation season. And plants are, of course, competing for resources. So we have below ground resources, nutrient and water. And above ground, we have space and light. And in the end, these resources are determining if like a plant can flower and also when it's flowering. So I was interested in what is driving the changes in phenology, as you might have heard of, like that the phenology is shifting, and this might then cause like or disrupt plant pollinator interaction or stuff like this, for example. So, and the concept and expectation of the study, so the data I already collected, and I run into problems with my old master's or PhD or frequentist statistics approach. So
is phenology just phenotype stuff, or what does that mean?
Phenology is the development of an organism or of a plant in time. So for example, bud burst of trees or leaf out of trees, or the flowering, or when the seeds, the grains start to fill, if you think of corn and maize. So this is like phenology. It's sort of the developmental stage during your entire lifespan, sort of. Yeah, so anyway, so whenever there are questions and unclarities, just ask. So the above ground competition can be measured in 3 different ways. One is very easy. That's just the height of the canopy. The other one is also easy. That's the relative amount of light that penetrates to the surface, to the ground surface. That's also easy. And the other one is sort of the asymmetry. So the distribution of light within the meadow. So as you can see, for example, what we're doing in the end is just we have the height on the x-axis and the light on the y-axis, and we make just a linear model. And when the slope is flat, there is no competition. So the light is very symmetrically distributed in the entire vegetation structure. And if the slope gets more steeper, we have a higher competition for light and an asymmetric light distribution. And my expectation would, if you think of like the growing seasons or the number of days are increasing, the above ground competition is increasing, and at a certain point it's saturating. That is the expectation. And then we have different treatments, for example, fertilization or drought. And this then is changing the above ground competition, because plants have then this different amounts of resources available. For example, grow a little faster if they are fertilized and grow better, so there will be a stronger light competition in the end, and they will start earlier. And in the end, how is this translating to the onset of flower for different species? That's sort of the idea. So drought delays it and fertilization advances it, for example. If you then look at the first results of the height, so the canopy height of the plots we've measured is increasing and saturating. That's not a big surprise. That's how plants are growing over the season. The light availability at the ground level, just like a relative amount from what's coming at the top to at the bottom, is decreasing. That's also not a big surprise. But my major problem is with this light asymmetry over the time, because it doesn't show these S shape. In the beginning, it's increasing, but at a certain point, the slope gets more flat again. And in the end, I want to use, like, I was thinking of a model, how to like a Bayesian approach, how to model like this slope or this curve, and then link this to the phenology of different species. For example, that early flowering species are like always done with flowering at the peak of light competition. And therefore, I was thinking of a model which maybe looks something like this. It's a very ugly deck where we have a day of the year, then we have our different treatments, and in the end, we have plant height, which is influencing the above ground competition. But there are various problems in there. There's like one big demon. This is like, for example, the effects of drought. They are depending on the plant size. If you are a small plant, very at the beginning of the vegetation season, you don't need a lot of water. So if there is like a drought or reduced water availability, it still might be sufficient water. And it's also depending on temperature, because like with a higher temperature, we have higher evapotranspirative demands.
How many species do you have in your model?
It's experimental plant communities. It's real life outside data, but it's roughly between 12 and maybe 20 per square meter.
Okay, yeah, but there's not like an indicator variable for which of the plants you are.
Pardon?
Is there an indicator variable for which of the plants you are?
What do you mean by indicator variable for which of the plants I am?
So you're predicting plant height, right? And I'm presuming that you're also predicting it based on whether you are like a rose or like a fern or I'm not as much of a biologist as you.
Yeah. So we had experimental communities outside in the meadow. We had these different treatments applied to them, and we tracked the height and the phenology, and we measured the light over the course of the season. So I have like actual data to throw into a model. But my problem is that my frequent twist approaches are not really working, and then from these splines or stuff like this, and it's very hard to then in the end link these to the shifts in phenology, because it's like all these cut models. So I need like an entire model, which I then in the end can link to the shifts in phenology. That's sort of the.
Yeah, and that part, like the words make sense. Are you calculating this phenology per plant species or like in general?
Per plant species.
Yeah, okay. That's what I meant by having an indicator variable for which plant you were. Like,
yeah. We have like species ID, and we can also categorize them like species flowering early or flowering late, depending on, like, if you think of or look outside the window, I don't know, I can just see a tree outside your window, but maybe there's a meadow. Grasses normally are flowering later in the season than, for example, very tiny herbs, like forget-me-nots, stuff like this, for example. Yeah. So I think there's one daemon like this, which I think may be tameable via specific prior selection. For example, warming during the spring months might profit or might benefit the phenology, but during summertime might have negative effects, because then it's increasing the drought stress in the end. But there's also another problem, which is like, it's more like a horde of demons occurring, which is all these unobserved stuff, where I have no idea how to incorporate it in the model at all. So that's like the.
Sorry, is that World of Warcraft art?
Yeah,
I think so.
until the day rained fire. Yeah.
Oh,
The
the
very
Burning
Blizzard-centric.
Crusade.
It's also that's Diablo, you know. The
Yeah.
evidence.
Oh, true. True. No, I just my bias towards Burning Crusade is shown.
Yeah. So in the end, that's like the model I want to use, but just to get into these bias thinking and try to apply it. But like the very end idea of taking this course or learning this is like, because I'm in the transition from like a PhD student towards the postdoc. And I think there is more needed to look professional and more experienced than just get redressed, cut your hair, look more happy.
I think the left guy looks more like a postdoc.
This one, yeah. I don't know. I've passed these states, so
It both looks great.
now
the left guy definitely reminds me of one of our assistant professors over here.
yeah, sorry. It's me.
both are great. Both suit you, both styles. But yeah, I really appreciate the DAG approach that you've taken here. I'd be curious to see whether you end up with a Gell-Mann or Pearl approach.
It's haunted. Like it's confounded by these two things, so he will get a bias estimate, and that's something he has to live with.
Yeah, I will give it a try and have a look at the outcome, and then depending on the outcome, it will become like a impact factor 7 paper or more like an impact factor 0.7 paper. But I hope a paper anyway. All we need.
Bernd, this slide is, I mean, glorious. It's wonderful. But I just noticed there is a typo, so I just want to tell you in case you want to use the slide again. When you write own expertise in Seine.
Oh yeah, there's like the C missing. Yeah.
Oh, right. Just just for next time.
Yeah, I think I won't use this because of my very sad and picture on the left side.
Oh, I think it's really cool. It's really nice.
It's an amazing slide.
Yeah. No, but the ideas I want to apply bias in future is like these stuff like non-equilibrium dynamics and hysteresis, because I think therefore you don't have any opportunities for stuff like this in a frequentist approach. But yeah, so far it's in the Kinderschuhe. I don't know what Kinderschuhe is in English.
Oh God, I don't know. We could just say that right now this is just a brainchild of yours, and now it's all about making it a reality.
Yeah.
All right. I'll take over then with my very short excursion here into what I'm currently cooking up. So my PhD is, in theory, all focused around species interactions from co-occurrence data. So basically, I'm trying to answer the question of, if I'm a certain species, am I in any given location because I actually like the others? Or am I not in certain locations because the others hate me and I hate them? So this is all about mutualism and competition outcomes, and how we might be able to come to an understanding of these community assembly processes through very sparse biological data sets. Now, I say this is only my PhD project in theory because so far I've used the first roughly 14 months of my PhD to just work on other stuff. And now I'm finally getting around to this, but we'll get to what I've been working on so far and how this feeds into this. So first of all, I think I have to clarify what I mean by an interaction. When we talk of interactions in community ecology, there are two different approaches that we can take to try to understand what an interaction between two species might be, or between two individuals. One would be a fitness approach, which tries to identify the changes in fitness in a certain focal species that can be attributed to the presence and effect of some other species. We could also go with an occurrence approach, where we then look at changes in occurrence probability of a focal species, depending on presence of other species. So if we try to put this into really simple DAGs, basically without accounting for anything else, such as environment, trait space, phylogenies, we could just say that some other species, species A, would be interacting with our focal species B, hence shifting its fitness. So if species A would be a plant, species B might be an herbivore, because the herbivore eats the plant, thereby if species A, the plant is present, the fitness of species B, the herbivore, will increase. Now, if species A is a predator and species B is an herbivore, then of course, the presence of species A would decrease the fitness of species B because getting eaten isn't very good for fitness. This, unfortunately, requires a lot of biological information to tease apart because we need to know the fitness of these involved species here to try to understand how presence of one alters the fitness of the other. So this is a bit complex. However, people have come up with methodologies to address this, two of which are the ones that I'm focusing on in my PhD, revolve around the hierarchical modeling of species communities, or HMSC, or intrinsic fitness models. HMSC is a bit of a black box. It's highly complex. It can do a lot of stuff, but I still haven't gotten to the bottom of it. And I personally, at the moment, prefer intrinsic fitness models, and we'll get to why I prefer them on the next slide, if I'm not mistaken. I just want to complete this picture by looking at the occurrence approach, where basically we're just interested in how they depend on one another and how co-occurrence comes about between pairs of species. And in this setting, it is nigh impossible to get to a directed understanding. In DAG land, that is. So network-wise, we're probably talking about an undirected network now and not a DAG anymore, because it's difficult to try to tease this apart and say, if this is present, then probability of this being present increases, since you always only see them together or not. And that then just gives us competition. So this is difficult to identify in terms of directionality. And methodologies include mostly null models, where you just check co-occurrence probabilities against some randomly generated checkerboard patterns in landscapes, or joint species distribution models, which are a whole nother issue for a whole nother day. So what I've done is just simulate some networks. I have simulated some networks of species interactions, and from these simulated networks, I have then created data frames which just tell me fitness of a given species in a given location with a certain set of neighbors. And I basically just simulated many plots with many different species combinations, just wanting to get to an understanding of which of the established models in the fitness approach section can actually reconstruct basic simulated networks. What I've found so far is that so this is all about whether I can find a best practice method and might I be able to improve it. This is my simulated network, where you can see that we've got some negative effects of one species on another. So example here, species B has a really strong negative effect on species C, whereas species D has a really strong positive effect on species E, for example. Now, if I go in with the HMSC approach, I cannot reconstruct this at all. And I am currently not prepared to explain why that is, because as I said, I haven't gotten to the bottom of the black box that is the HMSC algorithm. However, what I have gotten to is run an already established method by a few researchers in Australia, the intrinsic fitness method, which, even though the nodes are in different positions right now in these plots, we can still see roughly the same effects as the ones that we had simulated. So this is the method that I have so far identified as working the best in really basic simulation studies. So how does it work and how can I improve it? And this is where we finally...
The intrinsic fitness thing, that has some prior information, where the HMSC is just like correlation thing, right?
And this is where we'll get to now, because this is where I can finally throw some formulae at you. I just wanted to make sure we're all on the same page. So this is what the intrinsic fitness method does so far. It tries to understand the fitness of a certain individual belonging to a certain species at any given site through a combination of some baseline fitness that is the same for all individuals of said species, explained by, and we add to that the effects of, and these are all additive effects, hence the summation symbol, of all of the different neighboring species that focal species which we're looking at with each individual observation ever encounters. Then there's some priors on all of this beautiful stuff. And basically, we're trying to understand if there are 9 individuals of species B at a given plot, how will that alter the fitness of species A at the same plot? That is what this method tries to answer. However, very importantly, this method was developed for very geographically constrained analyses. So what it doesn't take into account is bioclimatic niches, climate variability between different plots. There are no phylogenetic impacts in this model. And I think all of this could be done a lot better as soon as, and needs to be done a lot better, as soon as we go beyond the very small geographic ranges which this method was developed for. So what I want to do is account for climate parameters, and I do want to account for phylogenetic impacts.
What happens if you just assume it's a multivariate normal and you just look at the correlations in that matrix?
That would be where the phylogenetic stuff comes in, which is not what I'm going to show today because I wanted to keep this somewhat brief. So instead, I'm going to focus on climate stuff because this is what, but yes, Jan, thank you very much. This is exactly what I'm thinking as well. Multivariate normal on these parameters, chug some phylogenetic information in there, and we can see what that does to our fitness effects here, so the betas. But I want to talk about climate data because I have been basically devoting most of my PhD so far just to climate data. So what I propose one should change about this model, I've highlighted in green. First of all, I don't want to try to predict the fitness of a certain species at a certain plot by the number of neighbors belonging to a certain species, but by fitness of those. Because if we think about this, I might be doing really well as a certain species in a certain location, even though all of my competitors are numerous. But if my competitors aren't doing well, so their fitness is low, then of course I'll be doing well. But I as a species might be doing really badly at a certain location, even though my competitors are numerous, but they might be doing really well, hence they're suppressing myself. So I think that the number of competitors isn't actually the one proxy that we want to put into our linear model against our fitness outcome. I hope that makes sense. So that's why I'm substituting number of neighboring individuals belonging to a certain species by fitness of those individuals belonging to that
How is
species.
fitness measured?
Fitness, in my case, I'm working with plants, is measured as dry biomass. So how heavy do you get? And of course, that gets standardized so that the base fitness of every plant is measured as exactly 0. And then we just look at perturbations from that, because otherwise it's completely impossible to contrast shrubs against trees.
Yeah, so basically, so one of the things your model fixes is if there's one tree and a bunch of grass, then they're equally fit if they weigh the same.
Yes. Well, if they are both at their species average of fitness.
Yes, perfect. Okay.
Yeah. So I don't do Z scores across all biomasses at the same time. I'm doing them species by species by species.
And like it's basically like, so in this area, this plant is doing awesome here and not so awesome here. So it's like relative to the area you're measuring, right?
Yeah, exactly. So I'm blocking by sites and by species membership.
Yeah.
I am then adding to that my climate effects. So just another big summation of all of my different climate variables and parameters according to each climate parameter, according to each species, to try to understand the bioclimatic niche. So saying a species might be doing well in a certain location, not necessarily because there's a positive interaction with another species, but maybe just because that's the climate optimum, which will undoubtedly drive up the fitness that I observe of my species in question. The problem that I run into, however, is that with climate data, there is inherent uncertainty in the data itself. So we get dynamical uncertainty from climate reanalysis data sets. When we then downscale them to match our local climate regimes, we get statistical uncertainty. And without flying into too much of a rant here, if you ever work with any gridded climate data sets, all of these have uncertainty associated with them. Just all of them, except for the one that I've created with my R package, doesn't report the statistical uncertainty of the interpolation method used. And I think we need to work them into our actual models. Yeah. I mean, for biochemists, this must sound ludicrous. And it did so for my climate science co-author on what I developed here, because we have legitimately horrible climate data sets out there. WorldClim, looking at that one for anyone in the call who knows what that is, which are just not good in terms of data accuracy in comparison to the newer climate products, and also have incredible data uncertainty associated with them. But since the uncertainty is never reported, the uncertainty never goes into any model, and biologists always assume no uncertainty is reported, therefore certainty is 100%, which of course totally
seems right to me.
So
seems checks out.
So I want to work on that, and I want to implement the uncertainty that comes from the climate variables. By the way, the shape that you're seeing right now is the state in Germany that Richard just called in from. He is sitting right there. So this is what I want to work on. And this is where the base stuff comes in. I mentioned this in the beginning of this series. I think only Bernd and Sam were there for that when we talked about what we want to get out of this. And I said, I want to account for data uncertainty in my priors. And this is where adaptive priors come in, and also why I really wanted to know about reparameterization today. Yeah.
What do you mean with dynamic uncertainty? Do you mean like fluctuation over time? Or
right, sorry, yes, that is climate science jargon. When climate scientists run climate data models, they run multiple models at the same time. So usually they run an ensemble, as they call it, of 10 different climate models. These are different climate models with different initialization parameters. For each time step for which they then report climate data, they will build the mean of the ensemble members. So they have 10 layers, and they will average these out to give you the prediction.
So it's not fluctuation over time, it's just the variability of the different models they've used for predicting today's climate at position XY.
Exactly.
Okay, yeah.
Yes. Thank you very much, by the way. That was a much better explanation than I just came up with. So I'm going to be stealing yours and using that from now on when I need to explain dynamic uncertainty. Thank you. So here's what I'm proposing. Slap adaptive priors onto my shit. And the beauty is, I know the standard error for each location, for each time step, because I do have the dynamic and statistical uncertainty, which in terms of model are the exact same thing, and I can just stack them on top of each other. And I also know the mean data point, which is just my downscaled product or my observed climate data value. And now I can just let the model figure it out what the real value would probably be from all of the different data that I have. And I've got data sets with millions of entries. So I actually think that the model can learn a lot from these. Basically, all I'm doing is I'm doing adaptive priors. And then the covariance matrix will be my proposed solution for the phylogenetic stuff that I mentioned earlier. And that's it from my side. Went terribly over time here. But this is what I'm cooking, basically. I haven't run any of this, by the way, yet. This is just up here.
Yeah. your F should be like have a distribution sign, right?
Oh,
Your
yes.
Fi equals.
Yes, it absolutely should. Yes, you're right. Thank you.
But I think it's really, really smart. Like it's almost like a no-brainer to do this. So if it hasn't been done, I think it's also great that you're releasing a package for it.
Yeah. No, that's the beauty, because it hasn't been done, and because the package isn't out on CRAN yet, I still kind of have dibs on using the uncertainty in different biological aspects. So I'm trying to capitalize off of that as long as I can.
Yeah.
It is up on GitHub though, and I've got workshop material for that package on my website and everything, if anyone's interested.
Does your package work like for any climate data I put in there? Like right now I'm working with from the UK, these CRU-TS4, I think it came out
So
2020 last year.
What the package does is it has a few functions. To answer your question straight up, yes, it works with any spatial data set, because it's a basically two-step process. The first step that tell you what, I'm just going to go into a different presentation because I can explain this so much better just with flowcharts. So give me just 1 second, because I do have those down to a T by now. So let me just throw this into presenter view. And share the screen. There we go. So basically, this is what I've got, and I'll probably just go back to here. Right there. So this is what the package does. First, it has a function that lets you download climate data from the reanalysis data sets ERA5 and ERA5 land, which are currently the world leading climate reanalysis data sets for worldwide data queries. Now, local climate data sets, such as for the UK, which you're running with, might be better. I just have implemented ERA5 and ERA5 lands that we've got global coverage. Basically, you specify what you want for which region, from which data set, in what temporal resolution, because these come at hourly time steps. So my function does a bit of pre-aggregation of time step data before it spits the data back at you. So you don't need to deal with millions of raster layers on the final output. Then that's just what the data ends up looking like. Then we need some covariates for the interpolation that we're dealing with. By default, the package just uses a DEM, so a digital elevation model. But the workshop material that I've got prepared shows how to get third-party data in as well. And then it does the actual downscaling, which is done via a geostatistical interpolation method called kriging, which needs covariates, a target, and a training resolution, as well as your spatial product at training resolution, so that it can build some statistical relationships between the covariates as well as the climate data that you want to interpolate. And then it takes those statistical relationships and geospatially weighted extrapolates them from the existing data to a finer grid at target resolution, which then gives you the downscaled product as well as the downscaling error, which ends up looking something like this for surface air temperature across Scotland. And you can see that our uncertainty over here is incredibly tiny when compared to the actual range of predicted data values. And I have coded the package in such a way that at any of the first two steps here, you can input third-party data. So you can use any geospatial product for your climate data as a substitute instead of ERA5 or ERA5 land, and any other geospatial data product for your covariates.
Okay.
And if you want to chat about that, I'm more than happy to do so, but we should probably do that outside of the realm of this study group, because this isn't Bayes anymore.
Yeah, potentially. Like right now, my R is running at, I don't know, 25% from 1,500 species. So Yeah.
But yeah, I'd be more than happy to chat about that with you.
But I also got like comments to your prior talk, like once you said you are interested or you want to correct for the climatic variability between sites, but is this really necessary? Like both you as a species and your neighbors have at both of these sites the same climatic variability to experience, so there's no need to correct. Like if one site is very stable and the other site is very variable, then it doesn't need to be corrected because you are looking at the fitness of plants in this site versus in this site. So they need, in my eyes, I don't see the point to correct for differences in the variability, for example.
I see where you're coming from, but I think the key part here is that I have species which are present at multiple different sites. And if I am to get an understanding of how climate influences the fitness of these species, so that I'm in the end, basically you can think of this as though I'm trying to, like I have a big block of stone and I'm trying to chip away as much stuff so that only the true interactions of species are left. And one of these things that I'm trying to chip away at is the effect of climate onto the fitness of my species at different locations. And in order to get to that understanding, I would like to have, for my climate data, I would like to have the best understanding of the local climate data that I can get to.
So just throw everything in there, like seasonality whatsoever.
Probably, but not necessarily. But yes, very likely. I will undoubtedly end up with probably up to 20 climate parameters and then just do subset selection and see what works and what doesn't.
Yeah.
Because I'm running
in the book, like parameter selection, just throw everything in and do like a parameter selection based on R square.
Not quite like that, but yeah.
Why do parameter selection? Like because it's expensive to run the full model? Yeah.
Mostly because downscaling all of the climate data for all of the regions takes a fair bit of time. And I would like to just run a few test cases first to see what works for most species and then run bigger models.
Right. But that's okay, so it's just there's more than one climate data thing. There's like temperature and there's
Yes, so I'll have temperature, I'll have a measurement of extremes, both minimum and maximum of temperatures, because they are highly influential in driving species persistence and fitness, of course. There have to be water availability measurements. Some plants will be incredibly vulnerable to wind fields, you name it. Because I'm trying to automate a process here for up to 45,000 species in certain regions. I'm having a bit of an issue on just settling on a few specific climate parameters.
Going to correct for multicollinearity in your climate data?
Yeah, I don't quite know. I don't quite know how to approach that one yet. It's all on my radar, but I don't quite know how to deal with it yet.
So I have a clarification I would like you to make concerning the presentation. If you can go there, where you were talking about fitness approach and occurrence approach.
Sure thing. Give me just 1 second to open up the PowerPoint again. And then just slap that over here. There we go.
Okay, so I think this is the slide. So one thing that is a bit not so clear to me is because I've also been working with this HMSC package, the one you write here, the method under fitness approach. However, this package is described as a package that follows the joint species distribution model approach. So, and the essence of it is they created this package using normal priors and different parameters that they were able to estimate there. But the main goal for the package is to have some kind of co-association, or let's say interactions at the end using the residual posterior means residual of the that you are trying to model in this case, or probably you are using different approaches, like maybe you want traits also to be there as part of what you want to use, or you want phenological data to also be there. So I got confused when you separated them as if HMSC is no longer joint species distribution model. So that is one thing.
Yes, the reason I absolutely get your point, and you are completely right, of course. In the interest of trying to keep this as simple as possible, I lobbed HMSC in with the fitness approaches because HMSC can deal with actual fitness outcomes. That's why I put it to that side, because it can make use of that biological information, whereas joint species distribution models alone usually only ever take presence absence data points rather than actual fitness outcomes.
Okay.
That's why I put it to the left-hand side. Yes, HMSC is a lot more complex than what I'm showing here, but I didn't set out to explain HMSC.
May I have another point to ask?
Go for it.
You said you also want to include phylogeny into it, and I was wondering about your expectations for phylogeny. It would be like if species are phylogenetic closely related, would they try to rather keep away from each other? So the one is then reducing the fitness of the other one if they are closely related, or are they rather like increasing the fitness?
And I am absolutely not certain of what I'm going to see there. I read up a bit on this, and apparently it has been demonstrated that in nature you will find both. Something that's called phylogenetic attraction, as well as in other clades you will find phylogenetic repulsion.
Yeah, I think maybe there would need like an on-off switch variable. For example, if you think of like genera which have a very restricted geographic range, for example, like endemic plants on the Canary Islands, for example, you have like 30 or 40 different species of the same genera within a very small geographic range, but you only have them in this space. So I think in this location, they are definitely not negatively influencing the fitness of each other, because it's just the effect of these very fast and speciation processes. So if you think of the high latitude, and not high latitude, high altitude Andean sunflower or species.
Yeah.
But on the other hand, like if they are like generalist species, not endemics, then maybe there might be like these phylogenetic.
A little thing that I can add to that is from working with this HMSC package, I've come to realize that most of the data sets they apply the package to tend to give some kind of positive correlation to species that tend to have the same phylogenetic relationship. Like in the phylogenetic order, or three species that are closely related tend to have some kind of interactions based on the model in this case, compared to species that are less phylogenetically related in the tree, in the phylogenetic tree. So they cite an example of a bird species in Finland, and they use the phylogenetic trees of this bird species, and they found out that species that are close on the phylogenetic tree tend to interact positively more than species that are at the opposite end of the tree. I don't know if you understood my point there.
Yes, this is going to what I just mentioned with phylogenetic repulsion and attraction. And I'd strongly suggest that the case example that they've been running with in Finland is one of those examples of phylogenetic attraction, where because you share similar evolutionary history, you like the presence of each other and help each other out, basically, without trying to assign agency to plants here or animals.
Isn't a simple explanation that yesterday you were the same species, now you're a different species, you still have the same environment?
Yes, but unfortunately, there are also cases where the reverse is true, as in you were the same species, now you're different species, you're still in the same environment, but now you're competing.
Yeah.
And it's difficult for me, at least right now, to make a generalized statement about what's going to happen out there in nature. Because this is also my first time using phylogenies. I have no idea what's happening here.
At least they look nice.
Oh, true.
Like
yeah.
His sun, and then put some color in there, and lovely.
True.
Eric?
Yeah.
If I may ask a non-serious question, the first slide that you created, which package did you use for this big circle with all
for this monstrosity? That is an interaction network that I observed with the base intrinsic fitness method on temperate grasslands, savannas, and shrublands from the forest inventory analysis data set, and then piped all of the interaction coefficients into the iGraph package.
iGraph. So you use iGraph to make this?
Yes.
Nice. I think I will also probably try to use it for one of my presentations. Yeah.
Glad to hear you like it.
I'll have to leave soon to pick up another kid. But Anders Storm from DTU here in Denmark also, he's a Bayesian statistician who does phylogeny.
Cool. How about we take this quick heads up that Jan needs to leave in a second to put a stop to my ramblings about what I'm working on, and we'll have just a quick 5 to 10 minute discussion about what we'll do in the future with this group.
Yep.
Cool. I see some nodding. I heard a yep. Because I just first up, without getting too sappy, have to say that I greatly enjoyed the last few months with you guys, and I think we've built up quite a bit of a nice, tiny, tight-knit community here, and it'd be a shame if we just let it all disappear now. So I would be strongly in favor of staying in touch and trying to work out how we can still interact with one another. So what I would propose, and much of this is actually Jan's proposal here, would be to have monthly meetings instead of weekly ones. Just monthly get-togethers, and not highly structured like we've done so far, but mostly get-togethers in the sense of someone read something they found super interesting, someone has something they want to present to others, someone has a question. Now, of course, I realize that sometimes you will run into something, or you will want to share something, and you don't have necessarily the time to wait a month for feedback from your peers on it. So what I would propose, because I'm already using it quite a lot, and I know so is Sam and so is Ollie, is to use the platform Slack. Is anyone else using that already?
I am, but I'm a larger fan of Discord, but it's not a stone I want to die on.
I get that. I get that. Discord is very nice as well. This is mostly a who's already using Slack, and I guess we're in the majority. I'm also using Discord. I'm happy to connect on Discord with you as well, Jan.
So me, Serena, and Rojan are from the University of Bayes Discord.
Ah, right. So you're on a Discord then? Yeah,
on a Bayesian statistics Discord.
Right.
So actually, let me ask a quick question about Slack. So on Slack, if I usually use the browser. Mm-hmm. The main issue is that I can only check one channel, one group at a time.
Yeah.
If I use the app, can I check more than one?
Absolutely, you can. Let me quickly share my screen to show you how that works. So basically, we just share this. Right here, you can just see the landing page for our Oxford team. We've got all of our channels and then all of our conversations down here. And here on the left-hand side, you can see all of the other Slack channels that I'm a part of, which we've got. Now I'm already in a different Slack channel. Now I'm in a different Slack channel again. And I would just like to add another one to this, which we can then all funnel into. So yes, in the app, you can quickly switch between different Slack channels. And I would just personally really like to have everything integrated into one app that I'm already using religiously anyways. So what I would propose, unless there are super big concerns against it, or you have some really strong arguments for why we should all move to Discord instead, I would propose that we open up a Slack channel just for our base stuff, and we just keep inviting people who we think might be interested in it. So I don't envision this to be just the 7 of us and whoever's listening in the recording. I'm mostly thinking this is us putting together a nice space where we can discuss these things and potentially spin up additional study groups with base material, share interesting tidbits that we found, share questions, share concerns about what's going on in base land, and just connect.
So actually, you're thinking about two kind of different things in a way. So the Slack channel and the monthly meeting.
Yes. So the Slack channel would be there to substitute.
Is it in 1 hour?
Not substitute, but supplement the monthly meeting. Sorry, Jan, what did you say?
No, I said it was there for the questions. Is it in 1 hour, guys?
Sorry, I acoustically didn't get it.
No, it's just like what, like the class. It'll just be spammed with. Is it in 1 hour, guys?
Yeah, definitely.
And I think
yeah,
like one can easily post the questions or something, and not compulsorily that everybody answer at the same time, but whoever is so at that moment can answer the question. So I think that's the advantage of it, actually.
Yeah.
I think there's practically no difference between Slack and Discord.
I don't think there is either. No.
And if you're voting, I'm completely fine with you having 2 votes, Eric, since you're the one who's most active.
That's cool, thank you. And I was just about to come in with the but I'm creating it, so it's going to be Slack. So it is going to be Slack, and I'm going to prepare that channel probably later today, maybe tomorrow, and then just send round an invite via our mailing list. And I'll also send that to a few peeps who haven't been on the mailing list and who haven't been in this group. So feel free to pass it around as well. All right. I think we've reached the end then. We've got 2 minutes until our 3-hour time slot is up for this final meeting. Yeah, indeed, Jan. Thank you so much, guys. This has really been a blast. And I am already very much looking forward to meeting again in about a month or so. So I'll send around an update email with all of that later today, maybe tomorrow, and give you the date for our next meeting. And we'll wait for one of you guys to volunteer to lead the next meeting. Good stuff. Thank you very much, guys. See you around.
Thank you for all the work you put in.
Yeah, definitely.
It was awesome. Thank you.
It was a lot of fun. Thank you very much, guys. Bye.
I wrote a link to the blog post about the.
Already grabbed it. Thank you.
Yeah. All right. Perfect.